I have been dealing with fracture mechanics, with structural integrity, with polymers, and with additive manufacturing. And today afternoon, I am the chairman of this section. I wish you nice presentations and an intensive discussion. Don't forget 10 minutes discussion. Please be active. And it is an honor to introduce the first speaker, Sandra Pettersmann from the Montanuniversität Leoben from Austria. And she will start with her presentation, the session. Sandra, please, a very short introduction of your talk.
Thanks for your introduction. I wanted to add that I'm from the Material Science and Testing of Polymers Institute, and I will give a short introduction to my topic. We dealt with two semi-crystalline polymers in terms of the morphology and also the weld strength. We used for the process, we used fused filament fabrication, where the filament is just transported to the nozzle, it's molten, and it's deposited layer by layer on a build platform. We used polylactide, PLA, and polypropylene as they show a distinct morphology. PLA, as you can see here on the top, is amorphous when printed, and PP shows a high crystallinity, which yields to problems such as warpage and shrinkage. Therefore, we analyzed the two materials in terms of the degree of crystallinity for several different cooling rates, starting with 0.5 Kelvin per meter, going up to 16 Kelvin per minute. And we saw that for PLA, we reached a very high degree of crystallinity, over 50% for low cooling rates. And we reached an nearly amorphous structure at high cooling rates. So we have a very drastic decrease in the crystallinity. And for PP, we have not such a huge decrease, just a very low one, but we can see that we reach such big spherulites at low degrees of low cooling rates, and this small spherulite sizes and high number of spherulites for high degrees of cooling. So, and then we printed such 1 strand thick boxes, punched out tensile test specimens, analyzed them as they is, and also after different pros treatments. Take a look at the morphology with help of DSC and polarized optical microscopy, and also on the weld strength, where we did just perform tensile tests, and we pulled the samples apart between two single strands. So now you can ask me some questions, and if you don't have now questions, you can also always email me on the email above.
Thank you very much. Has somebody questions to Sandra? Please, Jürgen. And also then first Jürgen and then Jan.
Yeah, thanks for your nice presentation. Because in your experience, is the strength of a typical FFF sample more limited by the bulk material properties or by the interlaminar bond strength, also the interlaminar strength between the layers?
That's a really good question. We analyzed both, and it's really highly influenced by both of these values. So cannot say what's more important, but I think the interlaminar, so the welding of the two between the strands is really important, so that we can reach nearly the bulk material properties.
Yeah. And in terms of defects, I mean, because that was also discussed in previous talks, so the defects leading to a more fracture mechanical failure. So this is also something from your experience. Would you say it's more fracture mechanical problem, or more something related to a limited strength or reduced flow stresses in the material? How would you judge this issue?
In terms of voids, it's also for polymers a fracture mechanical problem, that's sure.
Okay, thanks.
Jan, you are the next.
Yeah, very nice talk, very interesting. You said you punched out those samples of this out of this block, right? So when you have the build platform, I assume that the build platform is hot, and you refer to the degree of crystallinity with respect to the cooling rate. Wouldn't the cooling rate change over the height of the sample? So in other words, wouldn't you have another degree of crystallinity at the very low, at the bottom of the sample, and another one at the top? Could you comment on that?
Yeah, that's right. We have another crystallinity at the bottom and the top, but I forgot to mention that these studies, the degree of crystallinity versus the cooling rate, we did on granulates. So we didn't do that on the printed sample. So we did it before we printed the sample. So yeah.
Mm-hmm.
Okay, so you're saying that the crystallinity basically of your tensile specimens should be always the same, because you assume one crystallinity at the midpoint of your C height, basically, right? Is that what you intend?
No, that's not what I intended. I just said that the DC measurements we measured on the granulate material, so not on the printed material. And we always did use the same heating rate, but different cooling rates. And if we would take a look at the crystallinity of the samples, of the printed samples from the bottom to the top of the sample, we would reach different crystallinities, but we then just can take a look at the first heating cycle, because this is giving the thermal history. If we then cool it down and heat it up again, the result should be the same for all heights.
All right.
Because then the thermal history is away, and yeah.
All right, cool, thank you.
Good. Are there other questions to Sandra? I have two short questions. One is about porosity. Did you measure the porosity in your samples?
In these samples, we didn't measure the porosity, but we also published another article where we compared PLA, PP, PETG, and PEAK, and we measured there the porosity. And it's then a question if we take a look at the overall porosity, because this was very low. It was around, I don't know, less than 1%. But if we then locally, the porosity can be higher. That's clear.
This would be the second question, the local porosity in the contacting and overlapping region of the two filaments, because this could be interesting.
Yeah, this is interesting, but we didn't take a look at this now in the study. But we should do it.
Yeah. This is not a sure do. This is only ideas. How can you improve collectively or strategies? Good, but thank you very much for your nice talk, and please also visit her YouTube channel and the entire presentation. And thank you very much.
Thanks.
Okay. Johannes, you are the next. The next speaker is also from Austria, but in this case from the Technical University Vienna, and he will report his research.
Yes, thank you. I'll try to share the screen.
Please.
And then we should be able to start. Just a second, right? Okay. Right, I hope you can see the slide now.
Yes.
Okay, perfect. Thank you.
Good.
Okay, let's move this to a laser pointer. Perfect. Okay, now we can start. Thanks again. So the topic of my presentation is bio-inspired toughening of composites in 3D printing. I tried for this short summary to include all of my information in one slide, so hopefully it's not too cramped here. But let's start on the top left side. So bio-inspired. So we got an idea from nature. This is a deep sea sponge, you can see, which lives on the ocean floor, and it filters the water. And what makes it so special for us is the mechanical properties of this sponge. So the mechanical properties of the skeleton, which is mainly made out of silicon dioxide, are significantly better than those of, let's say, average glass, because the skeleton of this sponge consists of 99% of this silicon dioxide and 1% of organic material. And this organic material is located as small lines between the small layers, sorry, between the layers of the glass material, of the bulk material. So we have a big amount of strong and stiff material separated by very, very thin layers of compliant organic material. And what this does is it actually increases the fracture toughness of the skeleton of this deep sea sponge, while also preserving the load-bearing capability and the stiffness and the strength. So how does it work? It's called the material inhomogeneity effect, which kind of is described on the bottom left part. You can see the light blue areas are the bulk material areas. So this is the strong and stiff material. And these are separated by very thin organic or compliant, in a more general way, compliant layers. And we have some, of course, there are always defects or voids or some kind of defects arising from statistically or from the production process, wherever. And if these cracks try to grow, they are kind of hindered by these organic layers or by these soft compliant material layers, and thus the fracture toughness increases. So that's the idea from nature, and we try to rebuild it with our 3D printing machine, which can be seen on the top right. So we combined the classical SLA, so stereolithography process, with an inkjet system, and by that we were able to produce a bulk material with the SLA process, which is kind of on the bottom side. So we have the liquid resin here in the vat, and it gets solidified by UV light. And after each layer of this strong and stiff resin layer, we have a very thin layer of inkjet droplets being placed here on the resin and solidified as well by UV light. And the inkjet layers represent the organic layers of the sponge. So this is a very soft and compliant material. And therefore we get this kind of laminated structure where we alternate the high strength and the high toughness material. And we produced some samples. Sorry, am I over the? Sorry, I will keep it short and simple. So we measured elongation at break, the impact strength, and the Young's modulus, and we can see that the elongation at break in the 3-point bending test and the impact strength in Dünstad impact strength tests rises significantly, while also the Young's modulus goes down, which is not very desirable in this case. Sorry if I've talked too long.
No problem. You have a nice study. Good. Thank you very much. The questions. Anton, please. And then Maximilian.
Thank you. Thanks for that presentation. I'm quite interested in the bio-inspiration side, and I'd like to hear your opinion about the layer thicknesses in the real natural living sample compared to your samples, and how this scaling might influence the observed properties, the actual thicknesses of these layers in the natural sample compared to your manufactured samples.
Yes, so in the sponge, so in the real world, these organic layers are measured between 5 or 10 nanometers, which is very, very thin. In our case, the organic layers, or the compliant layers which represent the organic layers, are about 10 or 7 to 10 micrometers, while the inorganic, so the resin, is 50 microns. So we are kind of not in that scenario from nature where we got like 99% of the one material and only 1% of the compliant. We have another ratio, but still the stiff and strong material is overall greater than the other.
Okay, yes, thank you.
The next, please.
Thank you, Johannes, for your presentation. 2 questions. One is, could you explain what exactly you compare in your graphs? I have troubles to relate the colors to what is happening. And if you say the Young's modulus, is it perpendicular, for instance, to the build direction, or in parallel?
Yes. Sorry for not mentioning the colors. What this means, this is due to a lack of time. So the pink one is the material, kind of the material representing the sponge, so with alternating layers. And the second column represents the bulk material, so only the bulk material without any inkjet layers in between. And the third one is actually a pre-mixed blend between the inkjet material and the resin. So all of it got kind of mixed in the vat and only printed by SLA. So we have, this was kind of to measure if the effect, if there was one, is due to the separated layers or just by mixing in some soft material. So what this actually tells us, the first two, or actually all of them, is that the effect comes from the separated layer and not from mixing the compliant material in the resin, and because the pre-mixed blend is nearly the same like the bulk material. And to your second question, the Young's modulus is perpendicular to the printed layers to get kind of the maximum effect of the soft layers.
All right, thank you.
Welcome.
And the last question, Sandra, please.
Just a short question. You mentioned that you evaluated the impact strength of the Dünstadt test in contrast to the Charpy test because of the build platform size. Can you say how big is it?
Yes, so the building platform of our SLA printer measures only 50 to 55 millimeters in the longest dimension. And so Charpy samples weren't possible to produce. So we settled for the smaller Dünstadt samples, which are only 10 millimeters in the longest direction.
Okay, thanks.
Welcome.
Okay, but in this case, you measured in the layer direction or in the transverse direction? What?
So the elongation break and the Young's modulus were measured by 3-point bending test and the impact strength by Dünstadt. And all of these measurements were, or the samples were positioned so that either the hammer of the impact strength tester or the indenter of or the setup of the 3-point bending test is perpendicular to the layers, or to the printing direction of the layers.
Mm-hmm. Okay. Thank you very much.
Welcome.
Yeah. We should change to the next speaker. Thank you again. Thank you for your nice talk. And,
thank you.
And we change, and I hope Florian is ready.
I hope so.
Florian Arbeiter is also from Leoben, from the Montan University from Austria, and he will present his study. Florian, please.
Yes, thank you. I hope you can hear me. I had some troubles with Zoom all day today, but I think it's working now.
I can hear you.
Perfect. Okay, so the topic I'm currently dealing with is basically similar to the other people in this session, is damage tolerance fracture properties. in additive manufacturing. And in our case, we're dealing with fused filament fabrication. And with this presentation, I just wanted to give a short overview of what has been done in the past and what I think is currently quite interesting or should also be considered in the future as well in more detail. So basically fused filament fabrication, since I'm not the first speaker today with this topic, I don't have to explain too much. Basically, it's a layer by layer build-up of specimens by using a small extruder and pushing a thermoplastic material, usually thermoplastic through die, and applying the individual layers. And due to the molten states, we usually get some sort of diffusion between the different layers. And with this diffusion, we build up our strength between the layers. And so far, most studies have been more or less focused on those two parts. So to print specimens and then see how strong this interlayer or intralayer, depending on the orientation, strength is. As mentioned in the discussion before, of course, porosity is always a big issue, since this is the study that Sandra Petersmann mentioned earlier, is where we did some micro-CT testing on different materials, where we can see that depending on the material, we have quite big differences, because this was also a question before. For example, with PLA, it is definitely a question of bulk strength, because with PLA, you can get up to 95% strength of the bulk material. For example, if you tweak your printing right with other materials, especially semi-crystalline, it's much lower. So then it's also other properties and parameters that are affecting our result much more. And usually what is also done in a technological approach is to have a look at, for example, okay, if I print in 0 degree and then test in 0 degree, or I print in 90 degree and test in this orientation and so on, how does this affect also my properties? But I would say this is about what most studies have been about so far. And what we are currently dealing with, or where we want to head our research in the future even more than is already the case, is, for example, to have a look at the more polymer-specific properties as well. For example, shown here, I think this was PVDF, a PVDF material printed in FFF, because we have, of course, still this huge dependence on testing speed, for example. So here, 10 by the power of -3 millimeters per second up to 10 by the power of 3 millimeters per second. We have quite significant differences in the properties we can expect. And also, of course, the fatigue behavior of polymeric materials produced by AM, which I think there will be a few more talks about later on, where we, for example, had a look at also the orientation dependent properties, where you can see here, if the crack grows parallel to the printing orientation, we get very nice crack kinetic rates, which we can test on several specimens, and they always yield the same results. Whereas, for example, if we print in perpendicular direction to the crack propagation direction, we can get quite interesting, I would say, crack propagation rates, because it actually is not really one crack growing continuously through the material often, but it can also be that the crack actually can feel, I use the term feel now, the next layers already. And because of this deposition, we have also difference in properties locally, and we get some very interesting crack initiation, propagation, stopping, initiation, propagation, stopping, and so on. And this can lead to quite interesting results as shown here. For example, the crack can grow still quite nicely through it, or we can get a mixture of crack deflection and propagation, so a nice mixture. And this is, for example, something that, of course, decreases your strength if you test the other direction, but it can significantly increase your lifetime if you tailor the interface just right. So it leads to a little delamination, but not too much. So, and with this, I'm already finished because my time is up already, I think.
Yes.
And I would be glad to answer any questions.
Okay, there is the first question, please.
Yes.
Jan.
Yeah. Okay. I have a question regarding your simple tensile specimens, the static tests,
Yes.
because I've seen this before. I'm guessing you're pulling the upper part of the specimen, right? And the lower one is fixed.
Usually, I would say yes.
Yeah.
I mean, we also have machines that pull down from the lower part, but in this case, I think it was up. Yeah.
Do you experience that the part is always failing on the top when you have a certain speed? When, like at the top, I mean, where
as shown, for example, here in this case,
Yeah.
you mean. At the higher speeds, I think it could be due to the shock waves. I'm not 100% sure. I would have to look up the fracture patterns to answer that question.
Because I see the same, and it's always at the region where you have basically the first layer that is on top, so to say. So there's this section that is the smallest section, and then where the first layer is bonded on the top, where it gets wider, this is where the fracture occurs. So
Okay.
you have actually a notch there. So
in this case, I can say no, that's not the case, because the samples, they were not printed like are shown here in Z direction, but they're actually, I just pulled them around to show them better, to fit more on my slide. They were printed in ±45 orientation. So that should not be the case. And for example, as seen here down, they fracture nicely in the middle. But yeah, as I said, it can be, the faster you test, you get some shock waves maybe in the specimen and could have an influence. But I think that's more Sultan's topic than mine. But in this case, but yeah, of course, you have notches all around your specimen usually, as if you don't use a perimeter, or if the perimeter is not tightly fit to the rest of the specimens. That we've also seen in some examples. Yeah.
It just was interesting to hear your opinion on this. Thank you.
Thank you.
The next, Jürgen.
Yeah, thanks for this presentation. So regarding lifetime, I mean, lifetime can be limited due to fatigue, for example, as you pointed out correctly. But lifetime is also somehow, especially in polymers, we have issues with creep. And do you see problems with these soft layers that you might significantly go up in toughness or fatigue resistance, but at the same time somehow kill your creep properties due to these soft layers, which usually have a lower glass transition temperature?
You will lose some properties there, definitely. I cannot answer it 100%. The tests for the creep are still running, or the creep fracture tests are still running at the moment. But yes, I would say you probably lose some creep resistance. From what we've seen so far, especially with the soft layers, also as in the talk before, one significant problem that we also have, that Ottmar, for example, Koletnik did not have to deal with so far, is the time dependency. Because, for example, the material inhomogeneity effect as a whole is highly dependent on the creep properties in polymers, on the static loads as well. Because if the creep factor differs, we get a different effectiveness of the material inhomogeneity effect. And of course, with the creep also comes the growing plastic zone sizes, which also alter the effects. So yes, that will definitely also influence the creep properties. I fear it will not be towards a better direction, but maybe worse. So I think in this whole topic, it will be boiled down to, you have to really know your application to decide whether to use those interfaces or interlayers in the future or not.
You can continue this discussion later or bilaterally. It would be a very, very exciting discussion. Thank you very much for your nice talk and slides, and also the answers. And we will move from Austria to Italy. I think Daniele is well prepared. He is coming from the University Padua, Italy, and he will report about his research. Daniele.
Hello, everybody. I'm sharing the slide. Yes.
Okay, very
good. Can you see the presentation?
Yes, I can see, and I can hear you. Perfect.
Thank you for the introduction, Mr. Chairman. So the work that I'm going to present you is it deals with a project that we have in collaboration with the Electrolux for reducing the waste of plastics in the white good industries. So in this work, we analyze the static and fatigue behavior of 3D printed virgin and recycled short glass fiber reinforced and mineral filled polypropylenes by using the so-called pellet additive manufacturing. That is basically a fused deposition modeling with pellets as raw materials. In the study, we analyzed two compounds. So the first one had the virgin polypropylene matrix filled then by a mineral filler and short glass fiber. The second compound was 100% of polypropylene matrix filled by the same concentration of the mineral and the short glass fiber. We analyzed, we compared two technologies, the pellet additive manufacturing with this process parameter and the injection molding. For the additive manufacturing specimen, we analyzed three infill strategies. So the F0 is as the filament parallel to the load direction, F90 normal to the load direction, and the infill strategy minus plus 45. So looking at the tensile test results, we see that for injection molding, that is the figure A, here we have an influence of the recycled polypropylene matrix on the, we have an effect of the recycling in the compound. As you see, the black curve is referred to the virgin compound, while the other curve is related to the recycled compound processed by injection molding. This effect of the recycling we have seen also for the additive manufacturing for the same infill pattern. So for here we have the F0 infill pattern, F19 and minus plus 45. And by comparing the technology, we see that the elastic properties of the F0 additive manufacturing specimens show comparable elastic properties with respect to the injection molded ones, but with lower tensile strength. We also observed a high anisotropy with respect to the infill strategies. And we see the same for the cycle compound, as you see in the figure C. Looking at the damage analysis, we see pull-out and fabric matrix bonding in injection molded specimens, while for the additive manufacturing specimen, we see that the fracture always happen in a defect caused by the infill strategies, as you've seen for the computed tomography images. At the beginning of the fillet of the specimens, the extruder deposits some materials in the normal direction with respect to the load applied. For the 90 degrees specimen, we see at the bonding of adjacent filament fracture type, while for the minus plus 45, we see interlayer delamination between two adjacent layers.
Very good.
We have the,
you should conclude because we need
yes.
time for
So we observe also an effect of the recycling for injection molding versus recycled materials in the fatigue strength, and the same trend observed for the static tensile tests have been observed also for the fatigue strength of additive manufacturing specimens. We also analyzed the fiber length distribution and the orientation by computed tomography. So okay. With this, I conclude.
Thank you. You have nice images and slides. Please, question to Daniele. I have my first question. Did you investigate what is the reason, the difference between fresh and recycled material? Do you compare the pure neat matrices?
No, we carried out the test only in the composite material, not in the pure polypropylene matrix, and we didn't investigate the effect of the recycling in the net material.
Because I assume your industry partner would like to have the same quality as recycled material like the virgin, or?
Yes, probably yes.
That would be the dream. This is why we try to push recycling. Yeah. Okay, but Helen, your question.
Yes, thank you very much for your presentation. I was a bit interested. I work a lot with laser sintering, and there we try to mix powder material, so recycled material that was used during the build and virgin material. Is that also something that you will investigate, to mix virgin material with recycled material?
Yes, I mean the company is interested also in mixing the recycling and the virgin matrix, but here we have analyzed just the pure polypropylene matrix and the 100% polypropylene matrix. Yes. For our research, we didn't plan to carry out this kind of testing.
Okay, thank you. And then maybe another small question. You mentioned in your title that you use short glass fibers and then mineral fills. Could you elaborate a little bit more on that? The short glass fibers, in which size range are we talking?
Yes, about this filler, I cannot provide the percentage of weight of them because it's a sensitive information from the companies. Yes, I'm aware that this information could be very interesting in analyzing such material, but I cannot provide any other information about that.
Okay, no problem. Thank you.
Okay. Very sorry, the Electrolux is very sensitive. Good. Do you have another question? To Daniele? See you. No other question to your talk.
Maybe I have one short one. Sorry. So you see from this slide, you see a massive decrease in the Young's modulus also with your recycled fiber, right?
A reduction of the Young modulus in the injection molded ones?
Yeah.
Yes, just a bit reduction of the Young modulus is observed here in this bar chart. Yes. We didn't investigate deeply this effect, but yes, could be caused by the influence of recycling recycled matrix on these materials. Yes, the similar elastic properties we have observed in the in the virgin injection molded specimens and the F0 degrees additive manufacturing specimens, as you can see from this bar and this bar.
Do you think that is related to the fiber matrix bonding, or is it related to just simple material degradation?
No, I think that is both condition has a fiber well oriented in the load direction. So I think just in this case, the elastic properties is not surprising that are similar. Of course, for the additive manufacturing specimens, the fracture happened before with respect to the injection molded specimen due to the presence of defects induced by the process itself.
Okay, thank you very much for your presentation.
Thank you all.
And I hope the next speaker from the Cranfield University from the UK is here. Yes, Fei Yang He.
Yeah, I'm here. Can you hear me?
It is nice to see you.
Nice to see you.
Could you share your slide?
Yeah, okay. I will share my slides. Wait a second. Can you hear my slide?
Perfect. Yeah, change. Yes, very good. I can see. I hope everybody can see. You can start with your short talk.
Okay, so let me introduce my research briefly. Basically, my research investigated the effect of printing parameters on vertical-glass crack growth rate of FDM ABS under dynamic thermomechanical loads. Here, the dynamic loads means the stress range and frequency are time variable. And our research considered the 3 critical printing parameters, including rest orientation, nozzle size, and layer thickness. This table shows the values of them, and these values almost covers the common printing value ranges. Then the specimens with an initial crack were printed with these parameters combinations and carried out the tests under 3 different temperatures. And this figure shows the experimental setups. Basically, we used a shaker to excite the cantilever beam to resonance mode. The beam's displacement and crack depths were measured to develop our vertical crack growth rate model. Because the stress range and frequency are time variables, so we calculated the approximate stress intensity factor here with the acceleration amplitude measured at beam tip. We calculated the displacement amplitude, and from this displaced amplitude, we can calculate the bending moment at crack tip, and finally we calculated the stress at crack tip, and finally got to the stress intensity factor. So for the results, I just show one examples here. This we investigated the relationship between rest orientations and the fatigue crack growth rate. So here in this figure, we can show that we can see that X orientation has the lowest crack growth rate, Y orientation has the highest rate. And we can also calculate the Paris loss coefficient C and M as shown in this curve fitting figure. And for the reason of them, because the Y orientation specimen, the direction of porosity is the same as in initial crack, and it is also same as the potential crack path. So the crack growth is very quick, and also the bending stress is longitudinal and acts vertically on the orientation voids, which also accelerate the crack growth too. And because my research is still in progress, so I cannot show the exact results of nozzle size and layer thickness, but I can show some figures for the airfoils. For the airfoils difference of nozzle size, this figure shows the 0.8 millimeter nozzle size. You can see this thing is micro airfoils, and this is 0.6 millimeter nozzle size. You can see the distance between 2 airfoils is smaller. And this one is 0.4. And you can see in one cross section, there are more airfoils which can affect the vertical crack growth rate. Okay, let's go back to my presentation. So my future work will continue to investigate the nozzle size and the layer thickness in fact, and I will develop the empirical model for different printing parameters, and I will also determine the Paris loss coefficient for these parameters. Okay, thank you for listening. Any questions?
Okay, thank you very much. For fracture for the fatigue crack growth test, do you use CT specimens or?
No, just a cantilever beam, because in our tests, I have to change the frequency and I have to change the stress frequency and also stress range. And it's better to just use a cantilever beam to excite it on the resonance mode. So that means the load can change. Can be
like these
yes,
specimens.
like this, yes.
And how did you measure the crack length, the crack growth?
Okay, the crack depth is measured by a microscopy.
Mm-hmm. You had a kind of traveling microscope, and then you measure the crack length.
Yeah, like this. I use this like camera to measure it.
Mm-hmm. Okay. Next question to Fei Yang. Yes, Jan, please.
Maybe just a question out of curiosity, but with respect to, let's say, bulk plastic specimens, how much energy is spent in the crack initiation? Is it rather quick and you're running, like from a Paris curve, you're running into this stable propagation very soon, or is there a lot of energy spent in the initiation phase?
Sorry?
Like how fast is the crack initiation phase? Is it with respect to the bulk specimen, the bulk plastic?
I used the initial crack. The initial crack depth is 0.5 millimeters. So it's there's no crack initiation stage. It's just the crack growth stage in my test. And it's very fast.
Right, but for like how much energy would a crack initiation take in this case? Is that something to consider, or is it anyways very predictable where the crack initiates in such specimens?
Yeah, so I didn't consider the crack initiation stage.
Right.
This is a continuous, yes. Okay, good. Florian, please.
Yes, one quick question. So you showed here the number of cycles is 265. So these were rather short-term tests.
Yeah,
and did you also have a look at, for example, hysteretic heating? Because if a sample breaks in that little amount of cycles, I would expect it to get really hot, no?
Yeah, and here for this number of cycles, it's just a little crack propagation part, because the crack only grows maybe 0.2 millimeters. It's not finely fractured, so it's very small. And also because we operated the tests under you can see here under 50 Celsius degree, so the heat definitely will affect the crack growth rate. Yeah.
Mm-hmm. Okay.
Okay. Thank you for your talk and thank you for the questions. We are moving back to Italy.
Thank you.
Thank you. And Dario, yes, I can see you.
Yes, here I am.
But first of all, yes, very good. You can share your slides.
Yes.
And you are coming from, I think, Messina.
Yes.
Very good, yeah. Then from the University of Messina, and you will report about your research about fatigue. Oh, we have a lot of fatigue today.
Okay. Thank you, Mr. Chairman, for your introduction. In this work, we applied the infrared thermography to assess the damage initiation in polyamide 12 specimens obtained by selective laser sintering. The infrared thermography was applied both under static tensile test, and under fatigue test with a stepwise increase of the applied load. For the fatigue test, we applied the classical Risitano thermographic method in order to assess the fatigue limit in a rapid way. While for the static tensile test, we applied the static thermographic method to assess the limit stress. The static thermographic method is a rapid test methodology able to assess the macroscopic stress. It has the limit stress. It is the stress between the transition from phase 1 to phase 2 during a static tensile test, where in the first phase we see a linear decrement of the temperature following the thermoelastic law, while in the second phase some plasticization occurs within the material, so the linear trend it is not more followed. As for first, we perform static tensile tests on this kind of specimens, obtaining a Young modulus, an ultimate strain, and a yield modulus, a yield fracture strain different from the datasheet properties. And also we compare for the same material these properties with the literature. By observing the temperature trend during the static tensile test, we can observe the first linear phase with a linear decrease of the temperature and a second phase with a plateau region in the temperature signal. By performing the linear regression between these two regions and making the intersection, we can assess the limit stress. Secondly, we perform a series of stepwise fatigue tests with a stepwise increase of the applied stress level and registering the different stabilization temperature. We report the stabilization temperature versus the applied stress level, and by performing the linear regression of the stress level below the knee of the curve and above the knee, we can assess the fatigue limit of the material. Finally, we perform a failure analysis of the rupture surface, both under static failure and also on fatigue failure. As we can see, we have a defect of the order of 0.1, 0.2 millimeters. And while the static failure exhibit a ductile profile, the fatigue failure exhibit a brittle profile. In conclusion, we apply two energetic methodology, such as the static thermographic method and the thermographic method. And as you can see from the value reported in the slide, these values are in good agreement. And the point is that the static thermographic method could be used as a rapid test procedure to assess the fatigue properties of the material and the damage within the material, adopting a very limited number of specimens and in a few time. Considering also that in the additive manufacturing field, the process parameter change with the change, and also the mechanical properties of the material change with it. So it is necessary to have a tool to assess in a rapid way the fatigue properties of such materials. Thank you for your attention.
Okay, thank you very much. Florian.
Yes, thank you for this introduction to the thermographic method, which I was not aware of. My question, maybe I did not fully understand it, but what do you exactly mean by limit stress or fatigue limit? Do you really mean that at this stress level, you do not expect any failure anymore? So the classic definition of fatigue limit, or?
I personally call it fatigue limit, but it's they are near, because the limit stress is a damage stress that is observed during static tensile test, while the fatigue limit is assessed by fatigue test. But as in my research, I performed several comparisons between the static behavior and the fatigue behavior. I see that if I cyclically stress the material with the limit stress that I found with the static tensile test, I obtain fatigue failure. So they are very close value of the fatigue life of the material.
I have to admit, I'm still not 100% sure. So when you say fatigue limit, you do not mean that at this stress, nothing happens in fatigue anymore, because usually fatigue limit is what comes from metals and says, if you load at this stress, no failure will occur anymore. That's not what you mean.
But according to the work of Risitano, if we perform fatigue test under the value of the fatigue limit as assessed by the thermographic method, we don't see any failure of the material. The small temperature increment that you see is due to the internal damping, in particular for plastic material, such as the polyamide. But generally for steel, it is really uncommon to have such small temperature increment. So we see a very high temperature increment if we exceed the fatigue limit of the material.
But that's not really a fatigue limit then, is it? Because you're testing here at 50% strength of your material. And that's a typical number that you actually do tests where specimens still fail in polymers.
Yeah, but in that sense, this is a kind of thermomechanical fatigue limit where the temperature increase contributes significantly to the final fatigue, I think.
Yeah, so it's a switch between thermomechanically induced failure and purely mechanically induced failure, but you still would have failure.
Yes, but the temperature increment are not very high. So in order to prevent thermal failure of the specimens, it is clear that if we increase the applied stress level also with a low frequency, in such cases 1 Hertz, we obtain anyway an higher temperature increase. And it is an indicator of damage within the material.
Mm-hmm. Yeah, it could be. But how do you explain if you increase the amplitude, there is of course increase of the delta T, the temperature, but at higher loads, you have then a decrease of the temperature during the cyclic loading. And yeah, because it should be viscoelasticity, because you have hysteresis or whatever, and even a little bit plasticity. This is what I cannot at the moment understand, because your temperature curves, the blue curves, about or above 12 and 15, you see the increase of the temperature is coming from the increase of the load.
Yes.
Yeah, and then you have cyclic load at that level, and then you have a decrease of the temperature. Does it mean the specimens cool down?
Yes, in this case, because it is able to exchange it with the surrounding environment. As I say previously, we have to maintain the frequency very low. You have to consider that for metal, we usually test this kind of material at 10 or 20 Hertz. So it's difficult to see a decrease in the temperature, but we have a very linear stabilization temperature.
Okay, and you are in this case, you perform the test at 1 Hertz.
Yes, in order to prevent higher temperature increment. So the important phase is to assess the knee of the stabilization temperature versus stress curve.
Mm-hmm. Okay. If there is no other questions, thank you again for your nice presentation.
Thank you.
and we will continue and move to Belgium. And the next speaker is coming from the university, the Catholic University of Leuven. Helen, are you ready?
Yes, I will share my screen. Can you all see my screen now?
Yeah, this is like a Eurovision Song Contest. We changed the countries. Yeah, you are the representative of
Belgium,
the Flemish part of Belgium. Yeah.
Yes,
Very
indeed.
good. Please start with your talk.
Okay, thank you. So during my presentation, I discussed the difference in mechanical behavior of cloud beads reinforced polyamide 12 specimens produced by laser sintering and injection molding. And I will just do, yes, if it's, yes, okay. And so we did a comparison of a commercially existing composite material, polyamide 12 reinforced with glass beads, and we compared it for laser sintering and injection molding. But then we also compared the reinforced samples with unreinforced, also polyamide 12 laser sintered parts to really compare the quasi-static and dynamic behavior of the samples. So we did tensile tests and fatigue testing, which I also explained in my presentation on YouTube. And we created this big curve with it, this big SN curve, where we can see the fatigue performance of the polyamide 12, the regular, so unreinforced at the top, and then beneath the glass filled, so the glass bead filled polyamide 12. And from this study, we concluded that all the laser sintered samples, so both for the glass bead reinforced and unreinforced samples, they indicate a similar fatigue performance as conventionally produced samples, so for injection molding and compression molding of the same material. And then we also can conclude that although there is a significant increase in Young's modulus for the samples that were glass bead reinforced, they show inferior fatigue behavior compared to conventional laser sintered polyamide samples. And we think now it's because the glass beads that are used as reinforcement act as a crack initiation site, and this composite material for additive manufacturing there is a demand from industries like automotive and space that really need stronger materials with enhanced mechanical properties, but the composite material now available will not be suitable for them as they are used in application with cyclic loading, and therefore further research is needed towards fiber reinforced laser sintering, where we have an effective stress transfer towards the matrix material. Thank you very much. Are there any questions?
Yes, you have a nice environmental at your university, and several of your colleagues dealing with high level numerical mechanics and simulation. Did you perform simulations also to your study, or only experiments?
No, so we only did experiments. I think more the simulation guys are in another research team. So for this research, it was only testing and experiments.
Mm-hmm. Because it would be really exciting to see the difference first in the glass bed content, because you mentioned that, of course, the Young's modulus was increased. And what happens with the normal tensile strengths? Because it should be a balance. The Young's modulus will always increase, and the tensile strengths not. And this is the second question: what is the difference if you have I don't know, different aspect ratio glass fibers, and whether you can increase simultaneously also the Young's modulus and the strengths, and also the fatigue strengths. Good, but maybe a simulation would help to support the experimental strategy.
Yeah. Okay. Thank you.
Okay, Florian.
Yes, thank you. Could you maybe go back to the Wöhler diagram? It was a bit too fast for me. But I think you said that the injection molding with the glass fiber and the laser sintered, they were similar, right? Or did I get that wrong?
Yes, so they behave similar for the glass bead reinforced. And with that, I mean mostly the laser sintered parts in the X direction. So a flat on the build platform, as you can see, because then the laser sintered samples in the Z direction show a little lower decrease in fatigue performance.
Do you know how big are the glass beads?
No, it's a commercial and commercially available powder, but what I researched and what I could find is that those glass beads are in the same range as the powder particles, which are about 50 microns.
Okay, so maybe that's the reason why, because with the glass beads you introduce the same initial notch size maybe as you would have in the laser sintering anyway. Okay, thank you. Very nice.
That could be. Other comments or questions to the talk? Exchange. Okay, Maximilian.
Yes, Helen, thanks for the talk. Just one question. I'm not sure I caught whether you know the difference in failure mechanisms. You said at some point that, you see that the fatigue limits are way lower. And do you see this also in the failure mechanism when you look at the fracture surfaces? Can you pinpoint what the main reason would be?
So no, we actually did quite some analysis like hardness, density measurements, but we didn't focus for now on the fracture surface of the parts, but this is something that we are also planning maybe to do, as we also think that's a good direction to further investigate samples.
All right, thank you.
Okay, then thank you again for your talk. And we'll change to the next speaker, even from Austria, from the Technical University, Mojtaba. Can you hear me?
Yeah, I can hear you. Can you
Very
hear me?
good. It's
Okay,
nice to
fine.
see. It's nice to see you.
Nice to meet you too. Also, I'm trying to share my screen actually. So
You will talk about photopolymers.
exactly.
Very good.
Yeah. So let me just check how can I share this. You can't share my screen yet. You can't see my screen yet.
Not
Can
yet.
you?
But should work. Share screen, and because you have the permission, and
You might be able to see that.
yes, and if you change for the presentation, now the other because we see the other. You should invert. Yes, exactly.
Swap presentation. Can you see it right now?
Yes.
Is it in full screen? Okay,
In
fine.
full screen,
Sorry
but
for
it
the
is-
delay.
Technically, you are well prepared. Please.
Okay. Okay, fine. Thank you for watching this. My name is Mojtaba Ahmadi. I'm a PhD student at Technical University of Vienna, Institute of Material Science and Technology. I wanted to briefly take you through what we have been working in our group we're focusing on phase separation in methacrylate-based photopolymers, which is an approach to affect the toughness of photopolymers based on methacrylates. So our goal was to somehow resemble acrylonitrile butadiene styrene, which is a common thermoplast and offers very nice mechanical property and also toughness. And we have selected some ingredients that resemble this material well by focusing on two different photocurable resins based on hard and soft characteristics. One of them is bis-EMA, which is well known in dentistry industrial, and the other one is urethane acrylate, which is diluted in acrylonitrile butadiene styrene. So phase separation actually refers to the formation of some domains that get opaque after polymerization. So if we cure the samples due to the incompatibility of the components that we have in terms of polarity and rigidity, etc., we get these opaque materials. So which means high turbidity is a nice indication of phase separation in our material. There are several methods as well to characterize phase separation, but the best method that has been presented so far is based on atomic force microscopy in tapping mode, where we get some image based on contrasting mechanical properties. So for example, here we have distribution of the material and also the mechanical properties, and this is a well detailed image. We can also have unreacted monomer traces here. But the problem is, if you want to compare the effect of composition of the components of the ingredients we have in the system, we need to change some variables, and therefore we cannot compare the results of all AFM images in this mode to have a better, nice understanding of phase separation in those materials. So we cannot recognize all the phases actually quantitatively. So there are several parameters that can affect the AFM in this mode, and that makes us to go with another test, which is based on manipulation of the structure based on having a force distance curve at each pixel. So we apply a certain force and we get some results, which it can be based on adhesion force, adhesion energy, deformation, modulus, etc. And in this case, the results are based on actual values. They are quantitative values, and but the problem is we cannot see such details of the image that we get in tapping mode in this mode as well. As a result, briefly, I would say that we need to combine both these modes to have a clear understanding of phase separation. I don't know how much time I still have, but I will be happy to answer your questions. Thank you very much.
1 minute, you can.
Okay, but this is all I can explain. More if you have any question about any of these slides.
Okay. Good. Finished.
Yeah.
Perfect. Thank you very much.
Thank you.
And the audience, your comments and questions. I have one about the structure. If I see the AFM images, I see this is a kind of dispersed distribution of
the phases.
Of the phases.
Exactly. Yeah.
And at least visually, this is seems to be also random or near to random. But this is the question. Did you perform an analysis of the images about this kind of distribution of the particles?
We can. It depends on which image we're going to investigate. But at any case, we can perform some analysis measurements to see the morphology of the structure. So actually, in general, we can get two different mechanisms on two different morphologies in general. One of them is based on droplet-like separation, and the other one is based on interconnected structures. So in this case, it looks like most likely like a combination of these two. So we have droplet-like and also interconnected structures, and they need more investigations. Actually, we need to have something to compare, and all of them depends on which mode we actually use to as a basic for our investigations.
And can you control these two morphologies? Does it mean can you change with chemical composition or with the printing parameters that you have dispersed phase or this kind of co-continuous or clustered phase?
Yeah. Exactly. Yes? This is our question. The question is whether we can change or affect the structures or the morphology to have a better toughness. We assume that the formation of some domains, mostly the soft domains, are able to affect the toughness so that they can dissipate the crack propagation energy. So they will act as an obstacle in the path of crack, so they can dissipate the crack propagation energy and finally increase the toughness. So this is exactly what we are looking for, to be able to affect the structures, so the morphology by changing the composition, maybe the radiation intensities, maybe the percentage of photoinitiator, and the other parameters involved.
Good. This is not nice. Okay. Other comments or questions from the audience? Please, this. Okay, if not, then thank you again for your presentation and the answer. And we will move to the north. And the last speaker in this session is Joe.
Das war so schnell. Niemand hatte Fragen.
Oh.
Oh, yes, I'm here. Yes, I can hear you.
Yeah, I was too fast.
No, I'm not. I'm actually ready. Yes.
Yeah. Okay. Yeah.
Yes.
Okay. Good.
Yes.
You are from Trondheim.
Yes, I am. Yes. And NTNU. Yes.
Please.
Yes. If I can share my screen. Let's see. Yes. Okay. Can you see my screen now?
Yes, and if you change to the presentation modus, then.
Okay. Yes. Now it should be full screen.
Oh, very good. Full screen. Okay, please.
Okay. Yes. Unlike other candidates, I only prepared one slide for this short introduction because I thought there'll be more time for the question. But if you need, I can always go back to the original presentation. But anyway, so the topic of my research is thickness and the scale effect of mechanical properties of PLA specimen fabricated via FDM. So in this research, we basically investigated thickness and both thickness and the scale effect of the specimens. And for the thickness specimens, we chose the thickness of 4 sets, which is 1 millimeter, 3 millimeter, 5 millimeter, and 10 millimeter specimens. And the standard we have is the ASTM standard for the dog bone shaped specimen for the tensile specimens. Also, for the scale effect, since the standard specimen is with the thickness of 3 millimeter, then we scale it to 50%, which means that the length, the width, and the height is 50% of the original, and also 30%. And then we fabricate with those specimens with FDM printer with PLA filament. And then we did the uniaxial testing on all of them with also with the DIC, and also we get the results. So we found that for the thickness effect, if the thickness increase from 1 millimeter to 10 millimeter, then the ultimate tensile strength also increase, and as well as the elongation. And the similar phenomenon also applied for the scale effect, with the scale up scaling from 30% to 100%. Then the ultimate tensile strength, also the elongation and failure increases. So the reason behind this could be first, the first layer thickness influence, because as we know, for the FDM printer, for the first layer, even if we set the height to be 0.1 for example, but in actual printing, because this is the layer between the nozzle and the plant foam, so the actual layer thickness we have obtained is slightly thicker than it is. And according to the literature review, between the thickness of 0.1 and 0.3, if the thickness is increasing, then the mechanical properties like UTS or elongation is decreasing. And also it can also be the reason of the higher number of layers can result in higher number of temperature gradients, which can cause the influence as well. So yes, so this is basically my conclusion. Thank you. Any questions?
Yes, thank you. Do you have a specific application for your PLA specimens, or this is only a general, or this is a general study?
This is only a very fundamental general study of these specimens, because as I checked for the literature review, a lot of people have done this for the conventional manufacturing methods, but for the FDM, so a few people has done this before. So that's why when we do the testing, we need to have a standard size. So because if the size is different, especially for the thickness and other geometries, then the results could result differences. And especially for the 3D printing, and because there are some defects during the printing, like internal voids, and also the thermal distribution, it probably is not even with when printing on the plant form. So that can cause some of the issues as well. Mm-hmm. Yes.
Mm-hmm. Thank you. The next, Sarah.
Yes, thank you very much, Luca, for the nice overview. I had just a quick question out of curiosity. Sure. Whether you observed any effect of the thickness on the surface quality of your samples? Because the gradient of the temperature would be changing, there might have been some effect also on that.
Yeah, on the surface level, yes, that's the next phase we're going to do, because we're going to use the SEM to do analysis on the surface morphology to check whether this is the reason for that. Because so far, for that reason, it's just suspicion from the other literature review. So it's like it's not confirmed by the experimental yet.
Okay, I see.
Yeah.
Thank you.
Yeah.
Sandra?
So in terms of the scaling, you said that for a higher scales, you reached higher tensile strength. I wanted to know if you tested with the same testing speed or the same strain rate.
Yes. For the testing speed, we used 2 millimeter per minute. So all the specimens were tested under the same condition.
Okay, because when the length of the specimen changes, then also the strain rate is changed. Did you also take a look at that?
Sorry, say one more time.
When you change the length of your specimen, then also the strain rate changes. Did you also take a look at that?
Not in this case, because for all the specimens, we fabricated with the same printing process parameters, and for the testings we used the same strain rate for testing.
Okay, thanks.
Yeah. Okay, and Jan?
Yeah, I was wondering, did you also measure the density of it? Because it seems, at least from the pictures, it seems that the area of these manufactured voids is larger relatively to the size of the specimens when the specimens get smaller. Is that an observation that is correct?
Well, that's actually a good point. For the printing process parameter, actually, we spent some time to determine. I mean, not technically optimized, but in order to get the 100% infill as much as possible, while maintaining the smooth surface, because sometimes it's easily to get over extrusion and will cause some rough surface as well. So once this process is determined, and then we apply this to all the specimens, regardless of the thickness and the scale. So the picture you see, especially for I thought I was wondering, maybe you meant for this picture as it can look, maybe it has more defects by the others. Yes, it can be the reason. So that's the thing we're going to do to measure the exact density for each of the specimen to see whether if it's the same value or is the scale getting larger, then the density is also increasing as well. Yes.
Okay, thank you.
Thank you. There is a room for a last question. No last question to Loker? Then thank you again for your nice presentation and for the answers. And my special appreciation goes to all speakers of the session and also all contributing authors for these studies. I hope you enjoyed this session. We've seen a really nice presentation with different approaches. There is enough room for further bi or multilateral discussion. Use the frame of this conference and continue this discussion. And only my personal advice to all experimentalists, please also maybe discuss with your numerical simulation colleagues these aspects and maybe integrate them in further studies. Thank you again for your cooperation and for the organizers for preparing the nice technical background for this session. And I will close the session. Thank you. And don't forget, the conference will be continued at 4 p.m. with session 3. and Chiara will chair then the next this next section. Does it mean drink a coffee or tea and come back at 4 p.m. Thank you and goodbye.
Bye.
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 Yeah. Bye.
Bye.
Thank you.
Thank you.
Bye.
Good morning, good afternoon.
Hey, good morning.
Nice to meet you. I welcome Bettina Koch, Maximilian Sprengel, and we are waiting the other two speakers, Maria Jose Marquez, that is not here, and Luis Reis, or one of the team of Professor Reis. Welcome to Luis Reis.
Hi, good afternoon.
Hi.
How are
Good
you,
afternoon.
Chiara? Good afternoon.
Fine, thank you. Nice to meet you.
Nice to meet you too.
Is here Maria Jose Marquez? Okay, we can wait just another minute and then I will start.
Okay.
Okay, we can start. So as you can see from the share screen, I can welcome the speaker and the audience to the section 3, characterization of ceramic, polymeric and metallic material of ASEAM 21, the second European Conference on Structural Integrity and Additively Manufactured Material. I shortly present myself. I am Chiara Bertolin. I am Associate Professor in Non-Destructive Technique and Structural Health Monitoring at the Norwegian University of Science and Technology. And today I will be the chairman of this section that has 4 speakers: the engineer Bettina Koch, the Associate Professor Luis Reis, the PhD student Maximilian Sprengel, and Assistant Professor Maria Jose Marquez. Of course, you are already familiar with the format of the section, so you know that each speaker has 10 minutes time slot available. Within this time, each speaker will recall briefly the video presentation that uploaded some days ago. And then after the brief presentation, we will have time for a few questions. Now I will interrupt my share screen, and I will ask to Bettina Koch to please share her screen, her presentation. In the meantime, I will present her. So I'm glad to introduce the first speaker of the section. Welcome to Bettina Koch. She is an engineer from the Technical University of Vienna, Austria. She's studying at the Institute of Material Science and Technology and at the Institute of Applied Synthetic Chemistry at TUV. She will present her work titled Ink Development for the Fabrication of Digital Materials with Increased Fracture Toughness. Bettina, you can share the screen. Okay, perfect. Perfect.
Okay, thank you for the introduction. I will shortly summarize you my topic. And yeah, so the concept of my work of the ink development for fabrication of digital materials with increased fracture toughness was how the title already says, the fabrication of digital materials, which are a kind of composite material consisting of a hard matrix and a soft ink. And you can see the process, how it is fabricated in this video here. So first the matrix is printed by a SLA printer. And then in the next step, the platform turns around and the soft ink is applied by an inkjet printer. And our motivation for this approach is based on natural toughening mechanism. So for example, in glass sponge, there are also alternating layers of silica and organic material. And in this way, the crack propagation is stopped in the soft faces due to the shielding effect. And the shielding effect is due to literature effective if the difference in the elastic modulus of the two materials is higher than factor 5. And therefore, I developed a soft ink material based on the monofunctional monomer cyanoacyl acrylate mixed with a low amount of crosslinker to get an elastomer-like material. And this developed ink shows a low viscosity, it is stable in storage, and it shows a very high reactivity. And also the mechanical goals are reached. So it's a soft material with a glass transition temperature of 10 degrees. And it shows a high elongation at break of over 200%. Then this ink was used to print a digital material with 25 micrometer layer thickness of a matrix, and then 0, 1, or 2 inkjet cycles were applied. So 0 is of course only the matrix, which is the reference material, and then 2 different amounts of ink. And we conducted nano indentation measurements. And as you can see in the diagram, the layers are well visible. So we definitely get a layered structure, but unfortunately the factor between the hard and soft faces is only about factor 3 instead of 5, even if the difference of the pure matrix and the pure ink was nearly factor 1000. But nevertheless, we did tensile tests of the materials, and you can see in the diagram, the solid line is the best out of 6 measurements, and the X marks the average. And the best sample is the green one with 2 inkjet cycles. And compared with the blue material with the matrix, the tensile strength was only decreased by 21%, while the elongation at break was increased by 106%. And in this way, it was possible to increase the toughness up to 117%. So yeah, our goal to toughen the material was reached with the concept of digital materials in this way. Of course, there's still potential to improve it, but yeah, it was already quite good. So that was my summary. If you have any questions.
Thank you very much, Bettina. Yes, I ask to the audience first if there is any question, curiosity, please. Otherwise, I break the ice. So, Bettina, I have a question. What are the common applications for this type of digital material, and which type of commercial development exists for this material?
It was just a basic study on if it is possible to improve it, but I compared it with another soft ink. So my topic was just the development of the soft inks. So I compared it with Tango Plus from Stratasys. Mm-hmm. And the main difference is that we got with our ink a lower viscosity, and the reactivity is much higher. So the other, the Tango Plus is also a soft material, it has also a high elongation break, but these 2 points are the main difference to the commercially available.
Okay, thank you. There is a question from Jürgen Stampfl. Please, you can also put your video on if you want.
Oh, as Bettina, I mean, I'm also co-author, but just more comment. As Bettina, maybe you could explain why the contrast in elastic modulus is so low. So we expected more. So maybe you can comment on that and what might be done to increase this contrast in elastic modulus.
Yeah, so we think that the reason is that the cyanoethyl acrylate ink diffuses into the matrix, because it's with this cyano group, a quite polar molecule, and the matrix is also based on urethane metacrylate, so it's also quite polar. And we think that this is the reason that the ink diffuse into the matrix, and therefore the difference in the elastic modulus is not as high as expected. So we will think about more apolar monomers to improve the behavior.
Thank you. There is still time for the last very quick question from the audience. You can raise your hand. Yes, Florent, please.
Yes, hello, thank you for your presentation. In the video, you have shown that the thickness of the layer you have printed is not really precisely controlled. And I was wondering if this shows a high effect on the variability of the test. Because what's shown in this slide is one curve, but if the thickness of the layer is not well controlled, I'm expecting some variability on the testing.
So the thickness of the layers should be the same, because we have this 25 micrometer of the matrix, and then the inkjet cycle. And then, of course, the next matrix layer is not, again, this 25 micrometer, but the difference of 25 micrometer minus the ink thickness. And that should be for the whole sample the same.
Okay, thank you. And did you test the material in the opposite direction?
No, this was only the tensile test of this 5B specimen. So.
Okay, thank you.
Thank you again, Bettina, for your interesting talk. So we can progress further with the second speaker, that is Associate Professor Luis Reis. You can share the screen while I am introducing you. Dr. Reis graduated in mechanical engineering and received his PhD degree at Instituto Superior Técnico of the University of Lisbon. At the University of Lisbon, he's teaching, conducting, and coordinating research on several different fields, such as product design and development, mechanical design, mechanical characterization of material, structural integrity, and material selection. Today, he presents a talk titled Characterization of 3D printed ABS specimens under static and cyclic torsional loadings. Please.
Well, thank you, Chiara, for your kind introduction. Yes, I'm going to present a short presentation of our work regarding the characterization of 3D printing ABS specimens and then static and cyclic torsional loading. This aims to respond to the few studies presented in literature concerning the torsional cyclic loadings in ABS material. So here, just the Ultimaker 3D printer that we have used, and we have used also the green ABS filament. And here you can see the dimensions of our specimens. And we have also considered the build direction, as you can see, the vertical one orientation. So here some fixing printing parameters. Just call your attention for the infill density that we have higher value than 100% due to the overlap between the rasters. Here, well, we have used the Instron machine to perform the tests, also the monotonic and fatigue tests. And we have considered 6 combinations, which means we are considering 2 infill patterns. As you can see here, the concentric one and the zigzag pattern. And also we have considered 3 walls, 3 contours. So 1, 2, and 3 contours. So we have here this table to differentiate between the amount of walls and the patterns. And then we have performed the fatigue torsions also with the biaxial machine. And then we have also considered the use of a thermographic camera to control the heating, to control the temperature. And well, we have used the microscope to analyze the fractal surfaces. And well, the tests were performed at load control, R-1, room temperature, 5 Hertz frequency. Here I present the results of the obtained from the monotonic tests. Well, regarding the obtained curve, as you can see, the elastic properties seems not to be affected by the number of contours, also increasing the number of walls, as you can see, 1, 2, and 3 by these colors here. And in the picture, well, it seems beneficial for the concentric pattern, but not the opposite occurs when we are talking about the zigzag pattern. So in the overall, the zigzag pattern presents better performance than the concentric pattern. Well, another issue is the surface quality. So we have analyzed also this factor. And as you can see from the difference between the 1, 2, and 3 walls, 3 contours. So based on this, and also on the obtained results from the mechanical tests, the monotonic ones, well, we are going to use this Z2W configuration, let's say, to perform the fatigue tests. So here I present you obtained the results from fatigue tests so far. So the SN curve, we have obtained the R correlation of 0.9, as you can see here. And here, regarding this phase factor analysis, well, as you can see here, well, when you are talking about low stress values, we are meaning this part of the curve and the high stress levels here. So for the low stress levels, well, we reach this kind of fracture surface. So the crack starts here in the 90 degrees planes, consider the axis of the specimen. And well, we have also several secondary cracks, well, which means in the end, we have this kind of irregular fracture surface. And for higher stress levels, well, we reach this kind of, let's say, flat surface, fracture surface. Now talking about effects, so we have identified 3 different effects, as you can see here in these 3 pictures. So one related with the physical gap between the layers generated by the voids. Another one in the middle is related with the smaller and physical pores due to the entrapped gas caused by melting of the filament during extrusion. And also here in the third one, which are indication of the pores induced by bad fusion between deposit adjacent racers. Okay, just some remarks of what I have said before. And as future work, we are working now on the improvement of the roughness and surface quality using acetone vapor smoothing or also using the ironing process. Okay, thank you very much for your kind attention. I'm available for any question.
Thank you very much, Professor Reis. Is there any question from the audience? Yes, Maximilian, please.
Oh no, sorry, I was just clapping my hands.
Okay, sorry, one moment, because it's not easy to see all the participants. So, Jürgen, please.
Yeah, thanks for this nice presentation. I was also looking at ABS in terms of if you use it conventionally in injection molding. So what would be typical applications where ABS is used in static and cyclic loading, as in conventional polymer engineering?
You are asking me about one kind of application for this?
Yeah. So what is ABS the ideal material for such applications where you have fatigue problems in?
This work is based on my work performed by our master thesis, Carla Ferreira. And well, we don't think about a concrete product. So just to evaluate and this material obtained by this process and also in cyclic torsional loading, because we have made a literature review and we didn't find not so many studies regarding this kind of loading. So that's why we perform this type of tests.
Okay, thanks.
Welcome.
Other question? Otherwise, I have a short question. That is this one. Do you expect will change something in presence of a notch in a similar cylindric sample? Do you have some idea of what can happen?
Well, this type of defects are a kind of notches. So yes, that's why we are trying now to improve the surface finishing. And well, then we are going to model this kind of geometries of the defects, and we are going to study which are the best or the one satisfactory model that we can use just to consider the presence of the notch or a crack. So we are developing this kind of work.
Okay, thank you very much. Other question from the audience? Okay, I think that we can close your talk. Professor Reis, many thanks. Very interesting.
Thank you very much, Chiara, for your kind attention.
Welcome. And we can progress with the third speaker, that is Maximilian Sprengel. So the next speaker is Maximilian Sprengel, that can share the screen. He is PhD student at the Federal Institute for Material Research and Testing in Berlin, Germany. He holds a Master in Mechanical Engineering and a Bachelor of Science at Aachen University. Today, he presents his work on the relaxation of macroscopic residual stresses in laser powder bed fuse stainless steel 316L. Please, the floor is yours, Maximilian.
Thank you, Chiara, for the very nice introduction. So I will talk today about relaxation of macroscopic residual stresses, so type 1 residual stresses in laser powder bed fused stainless steel 316L. And I have a very brief summary, if this works, of my work, which is focused, or in the talk that I gave, it is twofold, looking at the relaxation that you obtain when applying different kinds of heat treatments. And also when starting from a blank, when you try to machine different kinds of testing geometries. So for instance, tensile samples or fatigue samples. And I'll first start off with results that I have from my own experiments, where we applied 450 degrees for 4 hours as a heat treatment and 800 degrees and 900 degrees. That I'm plotting here with results from literature. These the references are given in the actual talk. What we've seen is that for stainless steel 316L manufactured by laser powder bed fused by the laser powder bed fusion process, is that you have high residual stresses. This is also seen for other alloys, but for 316L, we have high tensile stress, residual stresses at the surface that are balanced with compressive stresses in the bulk. And if you want to reduce them, there are different ways. And normally what we see often in literature are heat treatment strategies that use temperatures that are, let's say, up to 600 degrees to avoid sensitization, so carbide precipitation. And what we did is that we also looked at 800 and 900 degrees because we were interested in the cellular structure of these alloys. And what we've seen with some other results is that with very low temperatures, around 450 degrees, we have a minor residual stress relaxation. But when we apply 800 to 900 degrees, we obtain let's say 75 to 86% of relaxation, which is also in good agreement with what is suggested for welded austenitic steels and ASM International. So even though we have a very different microstructure between conventionally and laser powder bed fused alloys, we still obtain a similar result on the relaxation. And when we manufacture different types of geometries, starting from a rectangular block, the good news is that if you go to let's say cylindrical geometries, so for instance tensile samples or high cycle fatigue samples, you obtain more or less a very similar type of relaxation, that the bulk residual stresses, so we're not talking about the surface residual stresses, are very much reduced. I'm aware now this is a very reduced slide of the findings and the conclusion, but yeah, I'm open for questions, and of course yeah, if you have any further discussion later on, we can talk. Thank you.
Thank you very much, Maximilian, for the very effective presentation. So is there any question from the audience? Please raise your hand or open your microphone. So if not, I have a small question. So in the video presentation, you have shown that to measure practically the residual stress, you use the neutron diffraction, non-destructive technique. So there is a reason why you selected that technique, and what are the main advantages and limitations for this kind of application?
Okay, so neutron diffraction is used when you want to determine non-destructively the triaxial residual stress with a very good spatial resolution in the bulk of the material. So when you use X-rays, you will be limited to the depth, and you won't have, let's say, yeah, you won't have the same good triaxial resolution. So when it comes to bulk residual stresses in, let's say, metallic materials, Newton diffraction is the way to go. One good advantage is, or a huge advantage, is that you can use the data for subsequent simulations, so to compare the experimental and simulation results. And also, what we tend to see is that when you determine the residual stresses at the surface, if you do it on, let's say, machine samples, you won't have the residual stress that is, let's say, obtained by the laser powder bed fusion process, but you will have a stress state in a machine surface. And by using neutron diffraction, we are able to observe or to determine how the stresses relax in a fully laser powder bed fused microstructure. I hope that was clear.
Yes, yeah, absolutely clear. Thank you. Florent, yes, please.
Yes, nice work. Thank you. If I understood correctly, your video, you played with the geometry of the specimen and you look at the effect on the residual stresses.
Mm-hmm.
You always kept the scanning strategy the same, right?
Exactly.
How dependent do you think that what you have observed, this is general if I change the scanning strategy from one sample to the other one?
So on the thermal, let's say on the thermal part, the relaxation is depending on the initial magnitudes of the residual stress. And we know that changing the scanning strategy will affect these magnitudes. So perhaps we won't get the same relaxation results from the thermal perspective. And I would say more or less the same, let's say the same answer on the, let's say, the mechanical relaxation, because we see that the scanning scanning strategy has a huge, let's say, huge impact on the residual stresses, and further testing effort would be needed. But I think when you do the study, you need to maintain some parameters the same. And yes, so for us, it was a scanning strategy. But you're right. I think in the next stage, it would be to have a look whether this is, let's say, applicable to other scanning strategies, or if you change other process parameters.
No, I think you did a good job. I was just asking because I was, like, you showed that there is a strong effect of reducing the cross section, not so much changing the height of the sample.
Mm-hmm.
So does it mean that these residual stresses in the building direction are mainly controlled by the time? Because if you keep the same lasing strategy, when you reduce the section, it means you also reduce the time in between. So the thermal history for a local point is highly changed, even if you keep the same scanning strategy.
I think there's a misunderstanding, because what we looked at is the residual stress in, let's say, cylindrical geometries that were extracted from let's say a blank specimen. So we built like tower specimens, if I can call them like this, rectangular specimens, and then we cut specimens out. So there's not a reduced, let's say, thermal input, because we manufactured net-shaped specimens. We extracted them.
Then I misunderstood, because I thought at the beginning of the talk you said that you kept them on the platform, and I missed that one. Thank you so much.
Yeah. I'm sorry if that came out the wrong way.
Thank you very much, Maximilian, for the clarification and the discussion. So we have now the last speaker. I ask to stop sharing, Maximilian.
Yes.
Thank you. The next speaker is Maria José Marques. She is assistant professor at the University of Porto in the Department of Physical Engineering, Faculty of Engineering. She works also at the Physics Center of the University of Coimbra. Maria Jose, you can start sharing the screen, and in the meantime, I will present you. And her activity has been directed towards the study of the genesis and influence of residual stresses on the in-service behavior of mechanical component using multi-technique, but currently she is particularly interested in the study of the mechanical properties of metallic components made by additive manufacturing. She will present the talk titled Residual Stress in IC 316L and 18 NI 300 steels produced by selective laser melting. Please.
Okay, thank you for your kind presentation. So I'm Maria Jose Marques. I will talk about residual stress in IZ316L and 18NE 300 steels produced by selective laser melting. So this work was also done by António Castanhola Batista, João Paulo Nobre from University of Coimbra, Filipe Fiorentin and Abilio Jesus from University of Porto. I'm only to present the major results of the presentation. If you want to understand, see all the results, please see the presentation that is in the program of this conference. Okay, so the motivation of this study is written here. As all you know, the additive manufacturing requires certain input heat levels to melt the power material in repetitive cycles of melting and solidification. So this process characteristic can result in unwanted residual stress, which may compromise the fatigue behavior. So the main objective of this study is to compare the residual stresses generated in sample with two different dimensions produced by selective laser melting with two different steel power, IZ316L and IZ18NE300 steel power. The obtained results will be used to validate a finite element model under development. If you want to see the results of this finite element model, please look at the session set Friday 10 that you will present. Abilio Jesus will present this study. So here you can see briefly the main selective laser parameters that was used to produce the sample. Here you can see the sample. So two steels, two different size. Here you can have the sample size of different samples. But to understanding the results, what we are talking about, please consider the capital letter L to the big sample and the S for the smaller one. The reference to the material, SS, it will be the stainless steel sample, where more it will mean that we are talking about the merging sample. So the residual stress results that I'm going to present were obtained at this kind of equipment in the University of Coimbra with two different radiation for each steel. Because stainless steel, the main phase is the austenitic, only the present phase is austenitic, and for the managing steel, we have martensite phase. So the sample, sorry, I'm going to keep the PowerPoint. Okay, so the residual stress were determined in this lateral surface and the top of surface of each sample in two different directions, the longitudinal direction and transversal direction. The results, concerning the results, and for both size sample and for both steels. Okay, here you have what is the big difference in the top of the sample steels. The constant values that you see in the IZ 316L samples. So here you can see more or less the same amount of residual stress. These stress are tensile, bigger in the transversal direction than in the longitudinal direction in this top surface. When we look at the results concerning the managing steel, is different. The residual stress decrease or increase from one hand to the other hand of the sample. It's not constant anymore, but they still are tensile residual stress in this surface, no matter what is the S sample or L sample. Okay, now if you look to the results obtained in a lateral surface for the smaller sample, we see different residual stress evolution of the residual stress. In the IZ316L sample, you continue to see always tensile stress in the longitudinal direction and a transversal direction. But when you look at the Merging steel, the results show that in Merging steel lateral surface, we have compressive residual stress and a higher residual stress in the transversal direction. And that depends on the dip that you are looking for the results. Here you can see 1, 2, 3, 4 red lines that help you to see the corresponding values of each point in all of these figures. Here, if we look at the results obtained in the larger sum for both steels, we have similar results. We see in the lateral surface, that one, that for austenitic steel, we have always in the longitudinal direction and transversal direction tensile stress, where for merging steel, you see compressive residual stress. You see also that in compressive residual stress, the compressive residual stress in the merging steel are higher in the region of the sample that are near the build plate. Okay, and it depends on where what points you are looking for, but it changes from the build plate to the upper surface. So I think we can conclude the major conclusion of all this work is that when you look after residual stress in the austenitic steel, you will see in the top in the lateral surface always the tensile residual stress, where this is not the case of the merging steel. In the lateral surface merging steel, for this kind of geometry, you will see compressive residual stress. That depends on the point that you are measuring. And I think it's all. The major conclusions are presented, and I thank you for your attention. If you have any question, please.
Thank you very much, Maria. I have already a question that was posed in the chat from Giovanni Bruno, but I would ask to Giovanni if it's possible that he is asking directly to Maria José.
Can you hear me?
Yes, a little bit. If you can increase the volume, is better, I think.
Only.
Is it better now?
Yeah, better. Thank you.
So the two questions are a little technical on the residual stress analysis. The first one is that you use a tilt of plus minus 42 degrees, but this means that you assume the linear behavior. So you assume no gradients, no texture, and if you go further in the sinus-squared psi plot, you can see this kind of effects. Especially, you can check whether the sigma 33 perpendicular to the surface is 0 or not.
We are using the sinus-squared psi, so it means that we are using hypothesis that the sigma z is 0 in that irradiated surface. So the mean penetration is about 5 microns. So you don't have and after there is another reason. We use the omega geometry. Okay, so you cannot reach an incident, a grazing incident, for instance, if you are thinking about that. Are you thinking about the grazing incident, isn't it?
No. I was thinking of using the psi mode and not the omega mode, because if you use the psi mode, you can reach higher angle and see if there is any gradient, because you could see the gradient. There are always subsurface gradients in additive manufactured material. That's why. And you just, you know, average them, but it's okay, it's okay.
But I can give you another information, which doesn't say that there isn't a gradient in this irradiated zone. That we have already made some deep profile. We are combining the electronic polishing and X-ray. And the difference in the first microns, they are not significant.
Good, okay, fine.
In the first microns, not after.
Yeah, well, of course, yeah. So the second question I had is that because I see very small base plate chunks, you chopped the base plate actually.
Yes.
Yeah, because we observed a strong relaxation if you chop the base plate. You relax the stress in the part. That was quite an interesting thing, because we made it exactly to make the sample handable on the diffractometer. But at the end, we observed that there was a strong difference. You did measure the samples also in the as-built.
In the as-built, no. We tried to cut long enough, we thought, from the sample, but otherwise you didn't reach the lateral surface.
Well,
how do you get, if you have 4 samples, how do you get to the lateral surfaces?
By neutron diffraction.
Okay. But even with the neutron diffraction, I think, or you produce 1 sample in each build plate.
No, but indeed, the thing is that using lab X-rays gives you no other option. You need to chop. The point is that you create anyway a relatively strong relaxation. So what you measure is an underestimation of the residual stress. I wouldn't use, for instance, those results for modeling to validate codes. You see what I mean? So but it's okay. It's okay. It's
in fact, the presentation that will be done Friday, the model, the numerical model, will give you higher residual stress levels.
So you have the explanation now.
Thank you. After I will ask you, please, the reference of this study, if you.
Okay. Yeah. Okay. Of course. Yeah.
Okay. Thank you. Thank you.
Absolutely. So you can exchange the references via chat. Thank you very much for this discussion. I think that we can conclude the section now. So I want to thank all the speakers and the participants to the section characterization of ceramic, polymeric and metallic material. This has been a very short section, of course, but very interesting. I hope you have enjoyed the discussion, and now there is a small break before to come back and be welcome at the plenary section with Professor McDonald. Thank you very much for the participation. Bye.
Thank you. Bye.
Thank you, Chiara.
Bye. Thank you.
Bye, Chiara. Bye.
Bye. Thank you.
Hello, Eric. Welcome.
Hey, how are you guys doing?
Yes, good. How are you?
Very good.
Yeah.
I mean, it's just had breakfast, so it's pretty early here, but not too bad.
Okay, perfect.
I've been watching.
So,
I've been watching talks in the last session. They were very fascinating.
So I think we can probably wait 5 minutes if the chairman agrees, so we can have more people connected. It was a long day, so probably someone will come now.
We will wait a few minutes. Thank you.
Yes. Hi, Anton.
Hi.
So we had I think we had an earthquake. You know, I'm right on the border of Mexico, and I'm way in the north, of course, so there's no earthquake here, but there was an earthquake, I guess, in Mexico City and on the coast.
Wow.
It's kind of terrifying, but I hope everything's okay there. I haven't heard yet what the results are. I guess it happened last night, like a 7.1.
Oh, it's a lot.
Yeah.
So people are connecting, which is good.
So we're just waiting a few more minutes for those of you that have just connected. I will make my introduction short. Okay, I think we've got enough people online, and I think we can get started with the session. If that's okay with the conference organizers.
Yes, go ahead. Yes.
Okay, perfect. Thank you. So my name is Anton du Plessis, and I'll be the chairman for this last session of the day. It's been a great conference today, and quite a varied topics and interesting topics, and it's been a great spread. and we're ending off on a high, I'm sure. So it's also an honor for me to be presenting the plenary speaker today, Professor Eric McDonald. He's got quite a pedigree, and I'm not going to go through all details. I just want to bring up some highlights. He's a Murchison Chair for Manufacturing at University of Texas at El Paso. He comes from a varied background with a doctoral degree in electronic engineering and various industry positions, faculty fellowships at national US labs, a paper in Science, which is still something impressive, but most importantly, in my mind, is he's been instrumental in the development and the growth of the Additive Manufacturing Journal, which is at the moment #1 in all of manufacturing, which has an impact factor of 11. So he has been quite key in developing that journal over the last years. And he's now editor-in-chief of the new sister journal, Additive Manufacturing Letters, which I'm sure he can tell you about. Working with Eric in the last few years on some research projects, I can tell you that he's quite open-minded and sees opportunities, which is quite nice. Has a broad way of thinking, and is very passionate about additive manufacturing, all additive manufacturing. So I'm 100% sure you will enjoy his presentation. So Eric, over to you.
Hey, thank you so much. It's an honor and privilege to be able to speak at the conference today. I know it's late for you guys, so I know you're probably fatigued, but I'll try and keep this as thought-provoking and entertaining as possible. In a conference about structural integrity, I think what I'm about to introduce sort of a montage of ideas over the last 20 years of doing research in AM, where we're inserting electronics or components into structures that have complex geometries. We're probably, well, in most cases, we're reducing the structural integrity, but adding programmability, sensing, actuation, and things like that. So I hope this is thought-provoking. And in some cases, we actually found that by embedding wires into polymer structures anyway, that they acted as a reinforcement agent and can actually improve the structural integrity. But here you see just some pictures, I think, that are interesting to me. They're just sort of photogenic, so I like to show them on the first slide. One's a microcontroller with a magnetometer on the left, and then was done for NASA Johnson Space Center, and then the other is a button where we never actually got that to work, but you can see that there's a piece of silicon which has about 10 million transistors on the top, and that's a microcontroller. So this is like a computer and a button kind of concept. And we've done pills, we've done small miniaturization of these sort of complex geometries with multifunctionality embedded. But in general, we went more in the other direction, trying to make larger satellite type components. And of course, I got to start. I know Anton just plugged this for me, but I'm going to do it again because I see the work in the last couple of sessions. Unfortunately, I didn't see the morning session because that was deep and early in the morning in the United States, but there's a lot of great work here. And I highly encourage you guys to submit your work to our journal. I mean, I'm biased, obviously, and there's a lot of great AM journals now, and I publish in all of them, or I try to anyway. But I certainly encourage you to come to this journal. The first journal, which has been around since 2014, is, like Anton had says, is that it has an impact factor of 11. We typically get about 10,000 words, and we're looking at 30 to 60 day, turnaround time. So pretty reasonable, but still larger, bigger work. And then Anton and I just started a new journal, which is related to this. It's also Elsevier. They're tied together, sibling journals, I guess, where we're looking at 4,000 words when you don't count the references. So sort of a medium to shorter papers that we want to try and with a single review cycle, either get a conditional accept or rejection within 30 days. And we're really trying to get that number down. I know as a researcher, it's very important for me when I have an idea that I think is important, that I want that idea captured in peer-reviewed literature as quickly as possible. And I've just had a lot of negative experiences in general where, an article got published after 3 years or something like that. And so we're highly sensitive to that. And again, if you have any questions, if you want to know about, formats of these articles or anything about the submission process, feel free to contact me directly for sure. And then this was something that our Dutch Elsevier office gave us recently for the big journal. We probably have published 3,000 or 4,000 articles, I think, since 2014. Maybe I'm wrong. We've had 7,000 that have come in, so it's got to be a lot less than that. Actually, it's probably like 1,500 that we've published. And they looked at the keywords of the published articles, and I thought it was just interesting to see this. You know, clearly metals is a big component. It's probably 60% of the articles in additive manufacturing were metal related, either DED or powder bed fusion. And you see some of the keywords: heat treatment, microstructure, stainless steel, and, you know, selective laser, melting, electron beam down here. So definitely a lot of metals, but then there's polymers over here as well. And the word functionality down here would probably be what I'm going to be talking about today, which is doing things to juice the structures. So you get a complex, mass customized, you know, unique geometry, but then you put into it components that provide other functionalities like optical, biological, electronic, electromagnetic. And I'm going to try and show in the next couple slides some of these ideas that we've pursued over the last 20 years. Some in polymers, primarily where we started because of the temperature constraints of a lot of electronics, but also ceramics in the last 5 years, and metals also. And so I hope you guys find this interesting, but it's certainly a departure from the conference in some ways. And then just to do a little geography lesson, El Paso is in Texas, which is the second biggest state in the United States after Alaska. But we're actually closer to LA and Southern California and New Mexico and Mexico than we are the rest of Texas, where the population's on the other side. And I spent 4 years in Youngstown, Ohio, which is right between Cleveland and Pittsburgh, two wonderful cities in the Midwest. And this is where we had a presidential initiative in 2012 by Barack Obama to put in a network of manufacturing institutes that were inspired by the Fraunhofers, where there's a public-private partnership where industry and the government put money in to try and solve manufacturing-related technology challenges. And the first of these in this network of institutes was America Makes, which was focused on additive manufacturing. And in El Paso, we received quite a bit of funding from this institute, and I eventually went to the backyard university, Youngstown State, in the same city to get closer to the mothership, so to speak. But in the pandemic, about a year ago, I returned back to El Paso. So one of the interesting salient features about El Paso versus Ohio is that the Mexican food here is much, much better. And if you can see behind me, you see the Bhutanese architecture of the university, which is interesting. It's Buddhist Himalayan architecture, the only example in the Western Hemisphere. But the mountains behind that is Ciudad Juarez in Chihuahua, Mexico. So we're just right on the border, which adds sort of makes it a culturally interesting place. And of course, you all have an open invitation if you're in this region of the United States to come and visit our labs, of course. So I think this one montage sort of shows the big picture of what I'm trying to do for the last 2 decades, is taking additive manufacturing, where you get these, you know, intricate, complex geometries that are unique and bespoke, and then introducing just a whole suite of other complementary manufacturing processes: subtractive, component placement, wire embedding, micro dispensing. And then you see just a wide range of interesting objects we made. In this case, this was not at UTEP. This is Oak Ridge National Labs, a part of the Department of Energy, and one of the best additive manufacturing facilities in the world, I would argue. And here they use electron beam melting to do a pneumatic prosthetic in a latticed, you know, weight savings format. And then there's lots of electronics. One that went into low Earth orbit. This piece, a facsimile of which was in the London Museum of Science. There was a 3D printing exhibit that had been championed by the University of Nottingham. There's a ceramic piece. And I'm going to try and show just a wide variety of things we tried to do with additive that I think really leverage this ability to build an object that's complex, but to have access to the intermediate layers as the object is being fabricated. So this was really early. This was actually published in 2013 at the SFF, but it was 2009 that we did this. We're doing it manually. You just saw a bearing go into structure. This is a Stratasys printer, and you have one structure inside of the other, freely rotating relative to the outer edge. And we're basically trying to make a motor, essentially. And by doing that, by inserting into cavities manually magnets, electromagnets, bearings, we basically create a working motor that comes out in the end of the printer and spins at like 8,000 RPM. This is the electromagnetic magnets, and we maintain registration. The one thing we were not able to do, my dream has always been to be able to press print, wake up the next day, open the door, and have a robot walk out or a UAV fly out. And one of the big challenges, at least in 2009, was that these were all in a heated build envelope, Stratasys Fortis systems. And that's dangerous to put a battery in those types of conditions because the battery, of course, has got energy storage and could explode. And so we had to, in this case, plug it in. And you'll see that happening right here, where there's a pulse width modulation signal that basically controls the speed of the motor, but that it works. And this video inspired quite a bit of funding for us, where we tried to automate a lot of these processes. And this was just an amazing student, Efrain Aguilera, who is in industry currently. But I can tell you that that led to this. This is funded by America Makes in 2013. You see 2 Stratasys printers. We were collaborating with Stratasys, and we had access to their proprietary software, so we could collaboratively print 2 printers, start on one layer, go to layer N, and then start N+1 in a different material in a different printer. And the robot's pretty cool looking, but it's really just a fancy conveyance system. But what's really important, where the magic is this third system here, which is a gantry that allows us to do this suite of other processes. So here we're doing machining so we can get non-integer layer thicknesses, which is important for antennas, and also to get smooth surfaces and intricate detail. Here you can see some of that. But you can also introduce copper foil, copper wire, electronics, components, printed circuit boards. We did, right here, you're going to see that we actually had pick and place, where we put a PCB into a cavity and then we printed over it. And really our dream had been to be able to get this system to do a satellite. Here you're doing wire embedding, ultrasonically vibrating the wire to selectively heat the wire and submerge it into the thermoplastic. And this was a way for us to get printed circuit board performance of plated copper, and be able to compete with traditional electronics in terms of that conductivity, but with 3D. And it turns out that those wires, once they're embedded, serve also as a mechanical feature. They provide a reinforcement agent, which was something that was sort of a serendipitous advantage. So when I went to Youngstown State, we started in stereolithography doing this type of work, but then went to material extrusion of thermoplastics because of the materials being higher performance. But what you see here then is carbon, which is just a sort of the cool younger brother of stereolithography. And it's basically shining a light from below, and that sets the geometry. And then later you put it into a UV cure, and at a higher temperature, maybe 100 Celsius, and you imbue the mechanical performance into the objects. You strengthen them. Well, one thing you can also do is you can take 2 of these pieces, put them together before the UV cure, and they consolidate. So we were exploring the idea of building a jigsaw puzzle, essentially, of objects, putting in components into the superficial surfaces before we did the assembly with complex mating surfaces. Here you see that Adidas and New Balance are both doing shoes. And it's interesting to me that when I think of 3D printing, I think, oh, if you're going to 3D print a shoe, then I want one for my left foot and my right foot after I scan them, so it's anatomically correct. But that's not really what they're pursuing. What they're doing is they're using 3D printing to do complex geometries, lattices that provide better energy return and better performance in the shoe. And I think the fact that they're doing shoes, I should also point out, is really a testament to the durability of these latest generation of materials that are now available. And these elastomers are really soft and just very durable. Here you can see this idea of a jigsaw puzzle where you're putting a group of parts together. They can be elastomers, but they can also be stiff materials. putting in components, and then the UV cure consolidates it into a structure. Here we put wires into a tensile bar, for instance, and this is an idea that we're pursuing, but it does require assembly. And so, you know, the dream for me has always been this press print and come back the next day to a robot. This is a little different. It's got its own challenges, and we're certainly looking at them. And then about 2 years ago, the National Football League in the United States, which of course is our football, is trying to reduce concussions and head injuries. And for the last 2 years, carbon has been played on our Sunday matches in the United States in several football helmets that have been, you know, formed and are customized to the player, but also have these complex geometries to redirect the energy and provide energy management. And here what you're seeing is I've added wires interlaced at 2 different layers to make a capacitor. And now this board is pretty big, but it can really be reduced to just a single piece of silicon and a coin cell. And you can see that we can get deformation sensing. We published this. Any green that you see here, green letters, is a publication we've done. It turns out the NFL isn't that interested in actually measuring the impacts because that can cause lawsuits and things like that. They just want to reduce the head injury. So I got to the final stage of this helmet challenge, but we did not get funding from the National Football League, unfortunately. We're going to try and do it again this year. And then one thing just for the PhD students and master students, you know, stodgy old school journals like the one I showed, the 2 that I showed previously for Elsevier are clearly forever going to be a part of the scientific method, right? Because it's peer review, and that's very important. But what's interesting is I put this video up like a year ago, and I got like over 100,000 views. And I've done this several times where I've gotten, I don't know if it's viral, because 100,000 is probably not enough to be considered viral, but it definitely got a broad audience. You know, Airbus, Apple, Boeing, a lot of different companies and locations. And it's just interesting to me that the next generation of researchers really needs to, you know, understand how to promote their research in the most effective manner. Peer review is never going away, but it's always going to take at least a month to do it. And generally, it'll probably be more like 9 months to get an idea out into the public. But with these social networks, you know, I think it's interesting that these ideas can be spread much more quickly. And it's just interesting. In some ways, maybe ideas are going to be stolen more often. I'm not sure, but it's a new world that we're entering with social media, and it needs to be monitored and leveraged when possible. Here's just a high-speed video. There you see the 2 wires that were interlaced into this. The material here is not commercially available. It's Rebound. It's what Formlabs is using in the New Balance shoe. And it's just a really amazing, very durable material. But I thought that was worth just showing because it sort of shows how this could actually be used as an integrated sensor for energy management. So I talked about that motor and how I wanted to do a robot. And 2 years ago in 2019, I co-hosted a conference in Santiago, Chile. And we had a French researcher, Alexis Morel, who was talking about doing batteries. And he had done these studies where he actually printed, you know, kind of 2.5D structures that provided energy storage. But then with simulation showed that with gyroidal structures, interdigitated, high surface area, anode cathode architectures, that you could really get high power performance, as well as make a battery that's application specific. Like it could be the frame of your glasses, for instance, or it could be the bus of a CubeSat, a small satellite. And so I ended up talking to Alexi and convincing him to come to UTEP under a Fulbright fellowship. And right now, we're hoping to find out this week if we end up winning a sodium ion project with NASA. We submitted a big proposal with Sandia National Labs to do lithium ion batteries. And it's just really interesting how this is getting a lot of attention, more than I would have expected. But this, I believe, is an area that additive could really provide some interesting, you know, leverage. And here's just some more views of it. We're going to be using 2-photon photopolymerization with different chemistries to try and do, you know, micro batteries. And we're also looking at just standard vat photopolymerization and material extrusion. And so I just think this is an exciting area that hopefully can generate some really interesting applications for additive. And again, you know, when I showed that system before with the robot, the idea was to do CubeSats, which are these small university space science satellites. And the ability then to, the one over here on the right is the University of New Mexico. It's a 6U CubeSat. So it's 20 by 30 by 10 centimeters. And you can just see it's a rat's nest of wires. And so a lot of people will say additive manufacturing provides complexity for free. And I guess that's debatable, but I think there's some truth to it. But what we were trying to do is provide the electronics for free by sucking them into the structure, maybe even improving the mechanical performance of the structure. And so these are some examples of doing that with solar panels and having the wiring harness actually be, you can't see it, but it's actually inside of this wall. And it was basically ultrasonically submerged in an intermediate layer. And we even went so far as to do propulsion. This is with a company called Busick, where they have basically this structure. It's coaxial copper with Teflon between them. If you put 4,000 volts across this in a vacuum, it will ablate. And it won't shoot you off to Mars, but it would be enough to make a CubeSat rotate, you know, control the attitude to maybe focus a camera back on Earth. And we published this with the team at NASA. And what's interesting is there's a lot of work doing printed electronics with conductive inks, and they have a lot of advantages. But one of the problems with them is they have low conductivity. So by embedding wires into this 3D printed structure, which encapsulated the propulsion, we were able to quickly get a pulse, a delta function of voltage onto this coaxial structure to make it work. And we never got funding for this, but I thought this was just a cool idea. And then probably, well, it's arguably the dumbest thing we've ever done with 3D printing was we made this little dice. They're all dead now. We're trying to resurrect this project and do it in ceramics. But the idea of a microcontroller accelerometer, and each face has LEDs, and we can monitor the accelerometer to determine when we're rolling and when we stop and come to rest. Looking at the 1G from gravity, you can tell which face is up, and you blink the lights to indicate that you got a 6 in this example. So, you know, we went to casinos thinking that this was going to be something where we could customize them, put a, you know, the casino name onto the side because it's all digitally driven. And we went to the casinos and said, hey, this is kind of a cool idea. You know, are you guys interested in this for like maybe your best customers or something along those lines? And they were like, well, you could, of course, spatially vary this to make it have a bias so that it would land on the 6 more often than the 1. And we're like, of course, that's the beauty of additive manufacturing. And of course, they just said, no, thank you. You know, we want dice that we can trust. And so this idea never really went anywhere, but we are trying to bring it back. And we've recently at Youngstown State, Pedro Cortez, very close collaborators, has been looking at plating, but more importantly, we're looking at alumina, which from an electrical standpoint is very good for high performance electronics. It has a high thermal conductivity to release the heat from the electronics, and at the same time, you know, great dielectric properties. And so I'll talk a little bit more about that in a second. And if you look at electromagnetics, antennas, okay, so if I think about 3D printing, 2 application areas I think are really important are electromagnetics, because you can make these complex geometries and you can make antennas like you've never been able to make them before, and thermal management, where you can embed microfluidic channels to, you know, pull the heat out of a system. But in electromagnetics, in that area, this graph shows the loss tangent, which is how much electromagnetic energy is absorbed in the material when a wave traverses through the material, and the dielectric constant, which affects the speed of light as it goes through the material. And generally speaking, the plastics, polymers that are available in 3D printing are just not that great. They're kind of up here. You really want to be below this line. And then depending on the application, you want really low dielectric constant or very high dielectric constant. And there's a couple of interesting cases. Zirconia is interesting. The XJet printer, material jetting out of Israel, along with lithos, stereolithography, can also do very intricate, detailed zirconia, and barium titanate. They have very high permittivities, and you can basically manipulate the speed of light by making lattices that are spatially varying. And so there's a lot of exciting applications. So between Youngstown State and UTEP, we're about to hopefully print an International Space Station. I'll talk about that a little bit later. We're looking at several different printers, Admatec out of the Netherlands, Boston Microfabrication in the US, X1, XJet, Lithos as well. And zirconia and alumina are what we're looking at now, but really we're interested in these very high temperature ceramics, which we're hoping to get to with better furnaces. And I think ceramics is just a really interesting area where there's a lot of potential applications. And well, I mentioned it before, we just wrote a proposal, Made in Space, which is now Redwire, just installed this stereolithography ceramic printer in the International Space Station. And of course, the idea is that with microgravity, you can lock in the particles with an even distribution, not worrying about the suspension, the floating, the sinking of the particles. And this was installed in October. This is the astronaut that did that. She just returned to Earth, I think, 2 months ago. And we're looking at printing battery components and ceramics in this printer by the end of the year. And we're real excited about that. And then this is just an example of what I think is really impressive. And this is XJet, which is material jetting, but I see lots of different printers that are getting to this sort of lattice level of 1 millimeter unit cells. And in this example, you're seeing a lattice that's uniformly distributed, but basically you can vary that density of the zirconia in this example, and the effective permittivity per unit cell can be raised or lowered based on that density. And then furthermore, if the unit cell is at least 10 times lower than the wavelength of whatever electromagnetic radiation you're maybe interested in, you can effectively do lenses. You can focus or defocus the energy in ways that we've never been able to do before. And here's an example. This was a plastic piece done in 2011 at the University of Arizona. And so the permittivity and the loss is much higher, but this is a Lundberg lens where it's really dense in the center and gets radially less dense as you go out. And if parallel electromagnetic waves come in, then you can get them focused on the other side, or you can do the other. This is Boston Microfabrication. You can see with a 1 millimeter unit cell, we're basically, spatially varying that density and effectively changing the speed of electromagnetic radiation in 3D space. And so I think there's just some really interesting things that are going on here. And we just published a couple of papers in this area too, unit cell estimation and also mechanical properties of material jetted zirconia. And Anton and I did this. This is actually his work at Stellenbosch University. The problem, obviously, ceramics are very difficult to print. And if you look at them, you get delamination and cracking internally. And so we saw this with a CT scan that they had done it in South Africa. And we basically investigated hot isostatic pressing to see if we could remove that. And here you see before HIP and after HIP, and at least to the resolution of the CT scan, the cracking's gone away. Lattices, however, because they're not as bulky, tend to do pretty well without getting cracking. But big bulky parts where you've got it debind and center deep inside away from a surface, this type of problem persists. But maybe with just some post-processing, it can be addressed. And then just a couple more electromagnetic applications. I guess Desktop Metal had a process that suggested they could do copper with complex geometries. In the end, we never got a part from them, but we had a PhD student come up with this fractal antenna concept, which was just a really pathologically complex structure, hard to make. And we thought, how many different processes could we try to build this, and then go to NASA Glenn in Ohio and try to evaluate the antenna properties. And it turns out that EOS M290 did really well with an aluminum, and that worked well. And X1 had a still infiltrated with bronze that they made for us. They shipped it to my house, and my 16-year-old daughter ran over it because it was right outside of our garage. So this is one of the antennas that was 3D printed. And you can see it broke, but it did pretty well, actually. And you see the tire tracks on the box even. It did deform a little bit, but it's sort of a testament to the strength of the next generation of materials across the board for additive. And yeah, we did many different processes, and we're hoping to continue to do more in Youngstown. This was an interesting concept. It's also a fractal, but it's a Sierpinski. It's basically a pyramid with, you know, basically every level of scale down, you sort of mimic the same geometry. But what's interesting is we use powder bed fusion to do a ship in the bottle concept, where we have an internal pyramid that is dielectrically isolated from an external pyramid, which is an irradiating surface. And we did this in the EOS, and these antennas actually worked pretty well. But Trumpf in Germany allowed us to print one in copper using their green laser system. And so we're about to publish a paper on that system, that antenna right now. It's actually been submitted a couple months ago. But I think that's, again, just a testament to the breadth of materials that are now available in metals, ceramics, and polymers. And then to switch things up a little bit, another thing I did, Ohio is known for casting and metal, you know, the Industrial Revolution alongside Manchester and Sheffield back in the 1870s. And in my previous university, we had an S-Max printer, which is a 3D printed sand printer for casting. Here you can see you can make a mold, you can stack them like Legos, and you have a sprue, you can pour some metal inside. And now you can do castings of geometries that you couldn't do before. So you get the benefits of additive, complex geometries, the unique mass customization, but you get the heritage of a age-old, 3,000-year-old manufacturing process. And so we've done a lot of work in this area, and it's just a fascinating area, I think. It's a big leverage point. But of course, what I do is I put electronics into things, generally speaking. And so this green piece right here is a core that would be suspended from above into a cavity of a larger mold that would fill with molten metal. And in it, you see two little Bluetooth sensors. And I'm like designing these sensors. I'm making my own that are smaller, and they're disposable. They're like $10, $20 US. And when that cavity fills with molten metal, these wireless sensors send data out that's unprecedented, and they survive for like 120 seconds, and then they're completely destroyed. But you can see that this has got some Bosch sensors in it. It's got temperature, pressure, humidity, rotation, vibration, and magnetic field. And we've done just a whole bunch of papers talking about different aspects of measuring things inside deep, remote locations inside of a sand mold and a sand core. And I think there's garnering a lot of attention in the foundry industry worldwide. And it's pretty exciting. Okay, so notice here, my phone is on the top. And in that phone, I'm actually talking to a Bluetooth sensor deep inside of this. This is magnesium. I'm an electrical engineer, so I didn't realize this was dangerous. But I guess magnesium is kind of a dangerous metal. But you're going to see, I'm going to walk around, and you're going to see my phone collecting data from deep, deep within this sand mold. And it's a lot of data. It's, you know, you can see if a core shifts, motion. You can see when the mold moves with a forklift. You see pressure, temperature, humidity. We're about to do volatile organic compounds also. And so I just think that the idea of having access to these molds or complex geometries at intermediate levels to embed sensors and other features, there's just huge opportunities that people aren't thinking about. And it's just a fascinating area. Then just quickly, this is another project I did with Anton, so I wanted to show it, but doing spatially varying lattices in metal is something we can do with casting now with sand. And one of the problems with it is that very often, if you're filling from the bottom, these cores will prematurely freeze. So I had an idea of actually putting a induction furnace coil around the mold to keep it molten, but also to provide Lorentz forces to push the metal up into the decreasing strut sizes of the lattice. And we never actually did this because it turns out that when you do these molds, it's very difficult to clean. So we did a study. These are different lattice cores that we put into that mold you just saw. And we did some CT scanning. We could see before they were cleaned, the unbound and bound sand, and then identify if unbound sand was remaining and deep within the smaller central locations of the core. And sure enough here, and this is something Anton had done for us, is you can see that there's missing struts up at the top, because that's where the struts get to their smallest size, and it's the most difficult to clean, particularly deep in the center of these. And so this was just a really fascinating problem that we had, and we ended up writing a paper about just understanding how difficult it was to clean these. So here is the core. This is the actual casting object that we want. This is a cross section. And then here you see that cross section, and you see that some of these different sections are still filled with unbound sand. And so I just think the opportunities to go after these really crazy geometries exist. And then there's just these other challenges that, I didn't even consider, that getting the sand out of these different areas is very difficult. And so the idea would probably be that this core needs to be a multi-part core, so you get easier, better access to the internal cavities. And then another thing, not necessarily talking about embedding electronics, but similar to that CT scan paper I just talked about, we're also looking a lot at process monitoring and bringing, advanced computer vision. And one of the things we did a couple of years ago was do stereo vision, high speed, where we're looking at trying to identify the speed, direction, and age of spatter coming off of laser powder bed fusion. It was sort of interesting. We did this histogram of the speed of the spatter we saw after 10 seconds. And you get this almost like Boltzmann constant or Boltzmann distribution. And it aligned with industry. I just thought that was kind of cool and interesting. I like to do computer vision. I think there's a lot of opportunities based on the fact that you could be printing 10 different objects digitally, and each object is a different geometry. That just adds a whole, level of complexity to process monitoring. But if you're using computer vision where it's geometry aware and you have the STL as a reference, there's just a lot of huge opportunities, I think, in process monitoring, obviously, for additive manufacturing. And then I'll do the one last thing. Oh, I think I'm almost out of time, but I'll make this quick. Worked with the University of Bremen, directed energy deposition, powder bed fusion, or directed energy deposition with powder blown laser. And what we tried to do was introduce a sensor that could survive the high temperatures of this laser cladding process. And we made basically tensile bars and inserts, this gray part. We sent the gray part to Germany. They screen printed on ceramic sensors, strain gauges. And you don't want to screen print because that requires a 2D plane. But eventually we will introduce extrusion to print the sensors directly onto maybe even a complex conformal surface. And then here you see they had a dielectric metallization, a red sensor, and then they covered that over with two connection points to actually measure this. And the idea was we wanted to measure strain and temperature with a very simple sensor during fabrication, but also afterwards in an end use application. And this is just a tensile bar, but you could imagine maybe a lattice where at one layer, all the struts would have a sensor that could be read through an RFID approach so that these things would sing back to you with different frequencies that would be proportional to the strain, or basically identify, an imminent failure, some sort of structural prognostics. And so here's just a quick video showing this, and this is all I got. But there you see the insert at the different stages. Here you see tensile bars with a cavity for that sensor. You see the sensor inserted, two wires coming out that we're reading over on this digital multimeter. We come in the CNC system and we do some stitch welding just to tie these two structures together. And you can see that the sensor reacts. And then some of the sensors were destroyed, actually about 80% of them. Here you see the spatters. We're actually putting another layer of metal on top to consolidate the structures together. And you definitely see activity here. This is after laser cladding. It looks pretty bad, but of course this is hybrid. This is directed energy deposition with CNC. So we machine them, get a pretty nice surface. And then we pulled them and measured after the fact. And so here you see the in situ data, which I think is fascinating. It's that chip in a bottle concept. We're able to measure from a specific point onward what happened in the structure by placing sensors into the structure. And then after the fact, we have an end use sensor in the tensile bar. And then this is supposed to be the next generation where we're doing a much more sophisticated sensor. We actually wanted to have a USB connection to make it a little bit more consumer friendly, I guess. And then finally, I'll just show you this as a segue to say that if anybody's in this part of the United States, you have an open invitation to come and talk about possible collaborations or other ideas. This is Bhutan. You're right near Tibet, Buddhist monastery, which inspires architecture of my university. The mountains here are Mexico and Ciudad Juarez. And these mountains in the other direction are the end of the Rocky Mountains in the United States. And with that, I will hand it over to any questions.
Thank you. Thank you very much for that great presentation. It's really a widespread of interesting topics. So we have time for a couple of questions from the audience. Feel free, don't be shy. And if you want to type it in the chat box, I can also work with that. So the floor is open for questions. I have a quick.
Oh,
okay. No, sorry. Go ahead, Maximilian.
Thanks, Eric, for the very interesting presentation. I was wondering, you've shown so many nice applications, and you've said, you mentioned that many were turned down by industry. But so what is still missing for these new ideas to be picked up by industry? Is it, let's say, the quality of the parts, or what is the main factor, you think?
Well, clearly the quality, the durability is a big issue. You know, we started with stereolithography. Those first pictures I showed you were done in the mid 2000s using, but they were relegated to photochemistry because it was stereolithography. But now those same processes are being used for shoes. So things are getting better. I've definitely seen everything moving in the right direction, but I do think it's quality and when you have like conductive inks that you print, there's the endurance, the fatigue of these inks, the conductivity of the inks, if you, the flexural endurance, I guess is what I should call it. I mean, there's a lot of challenges because you're dealing with very complex structures and being used in applications that have never been conceived of really before, except in the last couple of decades. And so it's just very early, but I think it's inevitable that at some point we're going to be, I mean, this makes some of my colleagues upset when I say this, but in some point, inevitably, humanity will be able to go and, people will go into their kitchen instead of getting the next Android or iPhone 55, and go to the Apple store to buy it. You're going to go to your kitchen, you're going to download the design and press print. It's, if you ever heard of the show Star Trek, it's a 1960s, science fiction show. And they had this thing called the replicator where you could just dial up any atomic structure they wanted. If you wanted a cup of tea or a hammer, you just pushed a button and it was produced. And I mean, we're a long way from that now, clearly, but I think this idea of controlling materials in 3 dimensions to make applications that weren't possible before is inevitable. And I do see that material choices are just getting better and better every year. Resolution, spatial resolution, and now, like with this conference, you guys are looking at the more, deeper into the fatigue of the materials. It's just fascinating. I think this industry is just ripe with a lot of potential. I don't know if that answers the question.
No, it does. It does. Thanks a lot.
I'm excited is what I guess I want to say.
It's a nice vision.
Yeah.
Thank you.
So actually my question was also related to that, but specifically about this Formlabs resin you were talking about for the New Balance shoe. Can you tell us about anything about that? It's not commercially available?
It's not commercially available, but I just contacted them and said, hey, I've got this lattice and I've got a cool idea. And they printed it for me for free, which was, I mean, so Formlabs seems like they're pretty open-minded to do some of the wacky things that I do, because conceivably some of the things I do could make a manufacturer not look as, put them in a good light, but I try not to do that. But in this case, because it's specifically for a customer, the New Balance, I don't think they allow that to be available, but I'm sure they've got other materials.
But the materials have improved a lot in recent years for that process. So
I really think exciting. So. Yeah, I think that it's a testament that they're being used in shoes, right? you're going to walk on them 100,000 times, you know, and so to me, that's a pretty brutal environment. And I just think the materials in general across the board in AM are getting much better.
Yeah, exactly. Are there any other questions from the audience? Don't know if I can see everybody here.
Hello, I have one question, Anton.
Yes, Javad.
Thank you for your presentation. The question is not directly related to the presentation or the talk that you had today, but it's something that I hear a lot, so I wanted to know your opinion about it. It's about the quality assurance of these AM parts. People sometimes ask, what is the best practice for mechanical characterization? Should we follow the standards that are already available for conventional materials, or should a new standard be in place to consider the possible challenges that we have with these AM parts? For example, ASTM suggests a specific radius of the samples for fatigue testing, and then if you fabricate the sample via AM and do the testing, the failure would happen in the greeting area. So I wanted to know your opinion on this. Thank you.
Gosh, yeah. So having really an electronics background, I've got to be careful not to say anything that because clearly this conference, you guys are looking at the most sophisticated failure mechanisms for additive manufacturing. I mean, I think standardization is just absolutely crucial for this, and having a manufacturing heritage that is improving, but still it's a pretty short heritage, right? It's a short lifetime for these, particularly for metal objects, but also ceramics. I think it's the biggest challenge we have, and is trying to come up with standards for making objects that are in safety critical applications, biomedical, aerospace. And I think, yeah, you're hitting on the most important point. I don't know if I have a good answer for it, but it's clearly why this conference is so important, right? That the structural integrity of materials, right? It's I think the most important thing. I think all the other ideas of improving spatial resolution and things like that will happen naturally, but that this is the most pressing point to really broaden the adoption for industry in safety critical applications. So it's an interesting question. I don't know if I can answer it well, but I think it's definitely important.
I think it's a long answer, and I think that's the reason for this conference. Is we need to improve our understanding of these materials and understand how to improve them, and we can take part in ASTM. There's the F42 and others, different groups of that. So it's those things also develop over time. So we have another question from Sarah. Go ahead.
Yes.
Hey, Sarah, how are you doing?
Fine, thank you. Thank you very much for the very nice presentation. My question is about your last few slides where you talked about sensorizing and hybrid additive manufacturing. I think this would be in line probably with the Internet of Things, where we are trying to connect different devices and try to make them, let's say, collect and share information. It's a very exciting topic, but considering the technological limitations and also the effect that they could have on the structural integrity of the parts, for example, like in this case, you're showing there is a cavity where the sensor should be inserted. Do you think we will see more of this, or this will remain very limited to specific additive manufacturing technologies, I guess, especially again for the temperature?
Yeah, well, okay, so the manufacturing problems, just because of the high temperature, that's one issue. And we're dealing with like ceramic inks in this case, so it's very limited at this point. And then on top of that, you're affecting the structural integrity by introducing the sensor. Yeah, both of those are legitimate problems with this idea. But you have access now to layers that you didn't have access if you did this as a forging or a casting. And so there's just new opportunities. And I'm not sure if this is going to be useful, but I think it's worth exploring. And it might spring other ideas that are related to it. You know, obviously doing a tensile bar is kind of a terrible, boring mechanical example. But if there were, you know, light weighting with lattices where you could somehow not even introduce a cavity, but put the sensors, print them into the sides of the struts while you're building the lattice. So you still have access to these sort of internal struts. That could be potentially useful. The idea of having a little RFID circuit so that the strain gauge is a resistor that affects the frequency of a response. If you shoot electromagnetic energy into the lattice, each of these sensors kind of sings back to you at a different frequency depending on the resistance of the sensor. And you could just ensure that, okay, there's no imminent failure that's about to occur. It's a good question. It's very early, and these are crazy, wacky ideas, to be honest. And will they have utility in industry? I'm not sure, but it's certainly, I think, worth it from the standpoint of universities to explore the idea, and see if we can squeeze something out of it. But it's an interesting question. You're pointing out all the problems with it, for sure, and there are a lot of problems.
There are many challenges, but there are a lot of opportunities as well.
I think so. Yeah.
Okay.
Thank you.
Thank you very much. If there's no more questions directly now, you can also contact Eric directly, of course.
Of course.
Thank you very much for all speakers of today. It's been a great first day of this conference. So I hereby close the session and this day. And please join us at 9 a.m. sharp European time tomorrow morning. We have another great day lined up. So thank you, everybody, and have a great off time. Thank you.
Thank you. Bye.
Okay.
Thank you.
Bye.
Bye.